In approximately 530 years before the Common Era, on the Greek island of Samos in the eastern Aegean Sea, two teams of workers began digging into opposite sides of a mountain. One team started from the south, near the ancient city of Pythagorean. The other team started from the north, over a kilometre away. They could not see each other. They could not hear each other. They were separated by more than 160 metres of solid limestone, and they were expected to meet in the middle. The task sounds simple enough to describe. Two tunnels dug toward each other, meeting underground. But the execution of this task, in the 6th century before the Common Era, without GPS, without laser surveying equipment, without sonar, without any of the technologies that modern engineers rely upon to align tunnels over long distances, was one of the most extraordinary engineering achievements of the ancient world. The two teams, working from opposite sides of Mount Kastro, guided only by the geometric and surveying knowledge that was available to them, dug through solid rock for approximately 8 years, and when their tunnels met, the horizontal alignment error was less than 2 meters and the vertical alignment error was less than 1 meter. The tunnels met. They connected. Water flowed through the completed tunnel from a spring on the north side of the mountain to the city on the south side. The tunnel was designed by an engineer named Eupalinos of Megara, and it was commissioned by the tyrant Polycrates, who ruled Samos during one of the most prosperous and most culturally brilliant periods in the island's history. The tunnel, which served as an aqueduct to supply fresh water to the city, was approximately 1,036 meters long, and it was dug through the mountain at an average height of approximately 1.8 meters and a width of approximately 1.8 meters, large enough for a man to walk through upright. The tunnel was one of the 3 great engineering works of the Samians that the Greek historian Herodotus described as the most impressive achievements of the Greek world, alongside the great temple of Hera and the harbour mole of Pythagorean. The question of how Eupalinos achieved this extraordinary feat of surveying and engineering has fascinated scholars, engineers, and historians for over a century, and the investigation of the tunnel has produced insights into the state of Greek mathematics, surveying, and engineering that have transformed our understanding of the technical capabilities of the ancient world. The tunnel is not merely an impressive hole in a mountain. It is a demonstration of applied mathematics at the highest level, a proof that the ancient Greeks possessed a practical understanding of geometry, of surveying, and of underground navigation that was far more advanced than the standard narrative of the history of engineering typically acknowledges. By the end of tonight, you are going to understand what the Tunnel of Eupalinos is, how it was built, what surveying techniques Eupalinos used to guide the two teams of diggers through the mountain, and what modern investigations have revealed about the specific mathematical and engineering methods that made this extraordinary achievement possible. You are going to learn about the specific challenges that Eupalinos faced, the specific solutions that he devised, and the specific evidence that the tunnel itself provides about the methods that were used. And you are going to confront a question that connects this ancient tunnel to the broader story of human engineering. How did a civilization that is typically associated with philosophy and art produce an engineering achievement that would challenge the capabilities of modern engineers, even with modern technology? Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The Tunnel of Eupalinos is one of the great engineering achievements of the ancient world, a work that demonstrates that the ancient Greeks possessed practical engineering capabilities that matched, and in some cases exceeded the capabilities that the standard history of technology credits to them. The tunnel has survived for over 2,500 years, its walls still standing, its alignment still accurate, its engineering still impressive to every modern engineer who examines it. The story of how it was built is a story of genius, of ambition, of mathematical precision, and of the human capacity to achieve the seemingly impossible through the disciplined application of knowledge to a practical problem. Now, let us begin. Consider what the achievement means in modern terms. Imagine that you are standing on one side of a mountain, and you are told to dig a tunnel that will connect with another tunnel being dug from the opposite side. You cannot see through the mountain. You cannot send a signal through the rock. You have no satellite positioning, no radio communication, no laser level. You have a plumb line, a straight edge, and the accumulated geometric knowledge of a civilization that has been studying the properties of triangles and angles for perhaps a century. You must calculate the direction, the slope, and the distance of your tunnel with such precision that it will meet the other tunnel more than 500 meters away, in the dark, in the rock, in the silence of the mountain's interior. That is what Eupalinos did, and he succeeded. The tunnel was not merely a technical achievement. It was a statement about the power of the human mind to overcome the limitations of the physical world, to see through mountains using mathematics, to navigate through darkness using geometry, to connect two points that are invisible to each other by the force of calculation alone. The tunnel is a monument to reason, to the conviction that the laws of geometry are not abstractions but practical tools that can be used to shape the physical world. The Greeks of the 6th century believed that mathematics described the structure of reality, and the tunnel of Eupalinos is the physical proof of that belief. To understand the tunnel of Eupalinos, we must first understand the island of Samos and the specific historical conditions that made the construction of the tunnel both necessary and possible. Samos, which lies in the eastern Aegean Sea, just off the coast of modern Turkey, was one of the most prosperous and most culturally significant islands in the Greek world during the 6th century before the Common Era. The island was a major centre of trade, of shipbuilding, of art, and of intellectual life, and its strategic position at the crossroads of the sea routes that connected Greece with Asia Minor and with the wider Mediterranean world made it one of the most important commercial and naval powers of the archaic Greek period. The ruler who commissioned the tunnel of Eupalinos was Polycrates, who seized power on Samos in approximately 538 before the Common Era, and who ruled the island as a tyrant, a sole ruler with absolute power, until his death in approximately 522 before the Common Era. Polycrates was one of the most ambitious and most successful rulers of the archaic Greek world, and his reign was characterized by an extraordinary program of public works, military expansion, and cultural patronage that transformed Samos into one of the leading powers of the Eastern Mediterranean. The public works program of Polycrates included 3 projects that the historian Herodotus, writing approximately a century later, described as the greatest engineering achievements of the Greek world. The first was the tunnel through the mountain, the aqueduct designed by Eupalinos, that is the subject of this episode. The second was the great temple of Hera, the Herion, which was one of the largest temples in the Greek world, with columns that stood approximately 20 meters tall and that enclosed a space of approximately 55 meters by 112 meters. The third was the harbour mole, a massive breakwater that extended into the sea to protect the harbour of Pythagorean from the waves and the currents of the open Aegean. The fact that Herodotus, who had travelled widely across the ancient world and who had seen the pyramids of Egypt, the walls of Babylon, and the other great monuments of the ancient Near East, regarded the engineering works of Samos as among the greatest achievements of the Greek world provides an important indication of the scale and the quality of the projects that Polycrates commissioned. The comparison with the monuments of Egypt and Mesopotamia, which were the products of far larger and far more wealthy civilizations, suggests that the engineering of Polycrates' Samos represented an extraordinary concentration of skill, resources, and ambition that was unusual even by the standards of the ancient world. The specific problem that the tunnel of Eupalinos was designed to solve was the water supply of the city of Pythagorean, which was located on the south coast of Samos, and which was the principal city and the primary harbour of the island. The city's location on the south coast meant that it was separated from the principal freshwater spring on the island, the spring of Agiades, which was located on the north side of Mount Kastro, the mountain that rises behind the city. The conventional solution to the water supply problem would have been to build an aqueduct that followed the contour of the mountain around its eastern or western end, carrying the water from the spring to the city by a route that avoided the mountain. The conventional solution would have been simpler, cheaper, and less risky than the tunnel, but it would also have been more vulnerable to enemy attack because an exposed aqueduct running along the surface of the ground could be easily cut or destroyed by an invading army. The decision to build the tunnel rather than a surface aqueduct was therefore a military decision as much as an engineering one. Polycrates, who faced threats from both the Persian Empire to the east and from rival Greek states to the west, understood that the water supply of his capital city was a strategic vulnerability that could be exploited by an enemy, and he chose to protect the water supply by routing it through a tunnel that would be invisible and inaccessible to an attacker. The tunnel was, in this sense, a dual-purpose infrastructure project, serving both the civilian purpose of supplying water to the city and the military purpose of protecting the water supply from enemy attack. The engineer who was commissioned to design and to build the tunnel was Eupalinos, who came from the city of Megara on the Greek mainland. The selection of Eupalinos, who was not a Samian but an outsider who was brought to the island specifically for this project, suggests that the engineering challenge of the tunnel was recognized as being beyond the capabilities of the local engineers, and that a specialist with specific experience in tunnel construction was needed. The fact that Eupalinos was brought from Megara, which was one of the most important engineering centers in the Greek world, suggests that his reputation was established, and that his specific expertise in tunnel construction or in surveying was recognized across the Greek world. The biography of Eupalinos is essentially unknown beyond the facts that he came from Megara and that he designed the tunnel on Samos. His name is preserved in the text of Herodotus, who describes him as Eupalinos' son of Naustrophus, a Megarian, and in an inscription that was found in the tunnel itself, but no other ancient source mentions him. The lack of biographical information about Eupalinos is typical of the treatment of engineers in the ancient Greek sources, which rarely provide detailed biographies of the craftsmen and the engineers whose work built the infrastructure of the Greek world, reserving their detailed attention for the philosophers, the poets, the politicians, and the generals whose activities were considered more worthy of historical record. The geological context of the tunnel provides important background for understanding the engineering challenges that Eupalinos faced. Mount Kastro, through which the tunnel was dug, is composed primarily of limestone, a sedimentary rock that is relatively soft and relatively uniform in its properties, making it suitable for tunneling, but also presenting specific challenges, including the tendency of limestone to dissolve in water, the presence of caves and voids within the rock that can disrupt the alignment of a tunnel, and the variability of the rock quality from one location to another. The geological survey of the mountain that Eupalinos would have needed to conduct before beginning the tunnel would have provided information about the type of rock, the dip and the strike of the geological strata, and the presence of any major geological features that might affect the alignment or the stability of the tunnel. The tools that were available to the ancient Greek tunnel diggers included iron picks, iron chisels, iron hammers, and various types of iron wedges that were used to split the rock along natural fracture planes. The rock was removed from the tunnel face by hand, loaded into baskets or onto wooden sledges, and carried or dragged to the tunnel entrance for disposal. The process was labor-intensive and slow, with an estimated advance rate of approximately 1 to 2 meters per month, depending on the hardness of the rock and the number of workers employed. The total excavation of the tunnel, which removed approximately 7,000 cubic meters of rock, would have required approximately 8 to 10 years of continuous work, consistent with the historical evidence that places the construction of the tunnel in the period of Polycrates' reign. The ventilation of the tunnel during construction was a significant challenge because the accumulation of dust and foul air in the confined space of the tunnel would have made it impossible for the workers to breathe unless fresh air was supplied. The ventilation of long tunnels was a well-known problem in the ancient world, and the standard solution was to sink vertical shafts from the surface to the tunnel at regular intervals, providing a natural circulation of air through the tunnel, driven by the temperature difference between the surface air and the tunnel air. However, The tunnel of Eupalinos does not have vertical ventilation shafts, which suggests that Eupalinos used a different method to ventilate the tunnel, possibly the use of fire at the tunnel entrance to create a convective current that drew fresh air through the tunnel, or the use of bellows or other mechanical devices to force air into the tunnel. The lighting of the tunnel during construction was another challenge, because the tunnel was dug deep within the mountain, far from any source of natural light. The standard method of lighting underground workspaces in the ancient world was the use of oil lamps, which burned olive oil or other vegetable oils, and which provided a dim but serviceable light that was sufficient for the close work of rock cutting. The consumption of oil by the lamps would have been significant over the years of construction, and the supply of oil to the tunnel face would have been a regular logistical requirement. The surveying techniques that Eupalinos used to guide the two teams of diggers through the mountain are the most fascinating and the most debated aspect of the tunnel's construction. The fundamental problem that Eupalinos had to solve was the alignment problem: how to ensure that the two tunnels, dug from opposite sides of the mountain, would meet in the middle at the correct horizontal and vertical position. Despite the fact that the two teams could not see each other and could not communicate directly, the solution to this problem required a precise knowledge of the geometry of the mountain, of the position of the two tunnel entrances relative to each other, and of the direction in which each tunnel should be dug in order to intersect with the other. The surveying instruments that were available to Eupalinos included the groma, a simple sighting device that was used to establish straight lines and right angles, and the chorobates, a long, level beam that was used to establish horizontal planes and to measure gradients. These instruments, while they were simple in their construction, were capable of providing the precise angular and level measurements that were needed for the alignment of the tunnel, provided that they were used with skill and with care. The specific technique that Eupalinos used to transfer the alignment from the surface of the mountain to the interior of the tunnel is the key question of the Eupalinos tunnel research, and the investigation of this question has produced several competing hypotheses that we will examine in detail. The broader context of Greek engineering in the Archaic period, the period from approximately 700 to 500 before the Common Era, provides essential background for understanding the specific achievement of the tunnel of Eupalinos. The Archaic period was a time of extraordinary energy and innovation in the Greek world, a period in which the Greek city-states were expanding their trade networks, founding colonies across the Mediterranean, developing new forms of political organization, and producing the intellectual revolution in philosophy, mathematics, and natural science that would lay the foundations for Western intellectual life. The engineering achievements of the archaic Greek period included the construction of monumental stone temples, the development of sophisticated harbour facilities, the construction of roads and bridges, the mining of silver and other metals, and the development of water supply systems that served the growing cities of the Greek world. The specific achievements of each city-state reflected the specific resources, the specific challenges, and the specific cultural values of each community, and the collective achievement of the archaic Greek engineering tradition was a body of practical knowledge and practical skill that was among the most advanced in the ancient world. The specific engineering tradition of the island of Samos, which was one of the most technically advanced communities in the archaic Greek world, provides the immediate context for the tunnel of Eupalinos. The Samians were renowned in the ancient world for their skill in engineering and in craftsmanship, and the ancient sources attribute several important technical innovations to Samian engineers and craftsmen. The historian Herodotus attributed the invention of the Greek trireme, the warship that was the principal naval weapon of the classical Greek world, to a Samian shipbuilder, and the Samians were also credited with innovations in bronze casting, in the construction of harbours, and in the design of long-range trading vessels. The economic prosperity of Samos during the reign of Polycrates, which was based on the island's strategic position at the crossroads of the Aegean trade routes, and on the revenues from piracy and from the control of maritime commerce, provided the financial resources that were needed for the ambitious program of public works that included the tunnel, the temple, and the harbour mole. The cost of the tunnel alone, which required the labour of hundreds of workers over a period of approximately 8 years, would have been substantial, and the fact that Polycrates was willing and able to fund the project is evidence of the extraordinary wealth that Samos enjoyed during his reign. The political structure of Polycrates' tyranny, which concentrated all political power and all economic resources in the hands of a single ruler, was a factor that enabled the construction of the tunnel, because the tyranny allowed Polycrates to mobilize the labor and the resources that were needed for the project, without the delays and the compromises that would have been necessary under a democratic or an oligarchic form of government. The efficiency of the tyranny in mobilizing resources for large-scale construction projects was recognized by the ancient sources, which noted that the great public works of the archaic period were typically commissioned by tyrants rather than by democratic assemblies, because the tyrants had the power and the will to invest the resources that were needed for ambitious engineering projects. The specific relationship between Eupalinos and Polycrates, which was the relationship between an expert engineer and a powerful patron, was a type of relationship that was common in the ancient world, and that was essential for the execution of major engineering projects. The patron provided the authority, the resources, and the political will that were needed for the project, while the engineer provided the technical knowledge, the design expertise, and the construction management that were needed to execute the project successfully. The success of the tunnel was the product of this partnership, and the credit for the achievement belongs to both the patron who commissioned it and the engineer who designed it. The specific hydraulic engineering of the water supply system that the tunnel served deserves detailed examination, because the tunnel was not an end in itself, but a component of a larger system that was designed to deliver water from the spring to the city. The spring of Agiades, which was the source of the water, was located on the north side of Mount Kastro, at an elevation that was approximately 55 meters above the level of the city on the south side. The water was collected at the spring and directed into an above-ground aqueduct that carried it to the north entrance of the tunnel, where it entered the tunnel and flowed through the water channel on the tunnel floor, through the mountain, and out of the south entrance, where it entered a distribution system that delivered it to the various parts of the city. The gradient of the water channel within the tunnel was designed to provide a steady, controlled flow of water through the mountain, fast enough to prevent stagnation, but slow enough to avoid erosion of the channel and the pipes. The gradient of approximately 4 centimeters per 100 meters, which was achieved with a high degree of precision, demonstrates a sophisticated understanding of the relationship between the slope of a channel and the flow rate of the water, a relationship that was well understood by the ancient engineers, and that was codified in the Roman period by the engineer Vitruvius in his treatise on architecture and engineering. The clay pipes that lined the water channel within the tunnel are another important engineering feature. The pipes, which were approximately 30 centimeters in diameter and which were joined end to end with clay or mortar seals, provided a smooth, watertight conduit for the water that protected it from contamination by the rock and the soil through which the tunnel passed. The use of clay pipes for water supply was a well-established technology in the ancient world, and the specific pipes that were used in the Eupalinos tunnel are consistent with the pipe-making technology of the 6th century, before the Common Era. The specific military context of Polycrates' reign provides essential understanding of why the tunnel was built as a military infrastructure project rather than merely as a civilian water supply. Polycrates, who maintained one of the largest navies in the eastern Mediterranean, with approximately 100 ships, including 40 pentaconters and the innovative Samaina, a new type of warship that was developed on Samos, was engaged in a complex web of alliances and rivalries that included relationships with the Egyptian pharaoh Amasis, with the Persian king Cambyses, and with the Spartan military state. The security of his capital city, including its water supply, was a strategic imperative that justified the enormous investment that the tunnel required. The vulnerability of surface aqueducts to military attack was well understood in the ancient world, and the destruction of an enemy's water supply was a standard tactic of ancient warfare. The Assyrian military manuals describe the deliberate destruction of water channels and irrigation systems as a weapon of war, and the Greek historian Thucydides describes several instances in which the besiegers of a city targeted its water supply as a means of forcing surrender. Polycrates' decision to protect the water supply of Pythagorean by routing it through a tunnel was therefore a prudent military decision that reflected the specific threats that Samos faced and specific vulnerabilities that the city's exposed position on the coast created. The harbour mole, which was the third of the great engineering works described by Herodotus, served a similar dual purpose, providing both commercial benefits by protecting the harbour from storms and from rough seas, and military benefits by creating a defended anchorage for Polycrates' fleet. The combination of the tunnel, the harbour mole, and the Temple of Hera, the religious centrepiece of the Samian state, created a comprehensive program of infrastructure investment that addressed the military, the commercial, and the religious needs of the island, and the program as a whole demonstrates the ambition and the sophistication of Polycrates' administration. The intellectual climate of Samos during the 6th century before the Common Era was one of extraordinary creativity and innovation, characterized by the presence on the island of some of the most important thinkers of the archaic Greek world. Pythagoras, the mathematician and philosopher whose theorem is one of the most famous results in the history of mathematics, was born on Samos and lived there during the early years of Polycrates' reign. Theodoros of Samos, an engineer and sculptor who was credited by the ancient sources with the invention of the level, the square, and the lathe, as well as with innovations in bronze casting and in the design of large-scale buildings, was a contemporary of Eupalinos and may have been associated with the same intellectual and technological milieu. The presence of these figures on the island during the period of the tunnel's constructions suggests that the intellectual and technological resources that were available on Samos were exceptional even by the standards of the archaic Greek world. The specific question of whether Theodoros of Samos, who was credited with the invention of the level, which is the instrument that would have been needed for the vertical alignment of the tunnel, had any involvement with the tunnel project, is one that has been speculated about by historians. The ancient sources do not explicitly connect Theodoros with the tunnel, and the connection between the two is based solely on the coincidence that both were active on Samos during the same period, and that Theodoros's credited inventions, the level and the square, are precisely the instruments that would have been needed for the tunnel's alignment. The coincidence is suggestive but not conclusive, and the specific relationship between Theodoros and the tunnel project remains a matter of speculation. The question of why Eupalinos chose to dig the tunnel from both ends simultaneously, rather than from one end only, is one that has been addressed by engineers who have analysed the strategic and the practical considerations that would have influenced this decision. The most obvious advantage of the two-entrance approach is that it halves the construction time, because two teams working simultaneously can complete the tunnel in approximately half the time that a single team would require, for a project that was expected to take approximately 8 to 10 years. The reduction in construction time would have been significant, particularly in the context of the military threats that Samos faced and that motivated the construction of the tunnel in the first place. The two-entrance approach also has the advantage of providing two sources of ventilation for the tunnel, because the air can circulate through the tunnel from one entrance to the other, driven by the temperature difference between the surface air and the tunnel air. This natural ventilation would have been important for the health and the safety of the tunnel workers, who would have been exposed to dust and to foul air during the rock-cutting process. The disadvantage of the two-entrance approach is that it introduces the alignment problem that we have described, because the two tunnels must meet in the middle and the alignment of the two tunnels must be maintained over a distance of approximately 500 meters in each direction. The alignment problem would not arise in a single entrance tunnel, because the tunnel would simply be dug in a straight line from the entrance to the desired exit point without the need to coordinate two separate excavations. The decision to accept the alignment challenge in exchange for the reduction in construction time suggests that Eupalinos was confident in his surveying abilities and that he judged the risk of a misalignment to be manageable. The question of whether Eupalinos had any prior experience with two-entrance tunnel construction before the Samos project is one that cannot be answered from the available evidence, but the existence of earlier two-entrance tunnels in the ancient Near East, including the Hezekiah tunnel, suggests that the technique was known in the ancient world, and that Eupalinos may have been aware of the prior examples, even if he had not personally participated in their construction. The specific religious context of the Tunnel of Eupalinos provides additional insight into the motivations and the cultural significance of the project. The island of Samos was one of the most important centers of the cult of Hera, the queen of the gods in the Greek pantheon, and the great temple of Hera, the Heraion, was one of the most sacred sites in the Greek world. The construction of the tunnel, which ensured the water supply of the city that served the temple and its pilgrims, can be seen as an act of devotion as well as an act of engineering, a demonstration of the ruler's commitment to the welfare of the sacred site and of the community that supported it. The relationship between religious devotion and engineering achievement was common in the ancient world, where the construction of temples, tombs, and other sacred structures was one of the primary drivers of engineering innovation. The pyramids of Egypt, the ziggurats of Mesopotamia, the temples of Greece, and the cathedrals of medieval Europe were all produced by the intersection of religious devotion and engineering skill, and the Tunnel of Eupalinos, which served both the sacred and the secular needs of the Samian community, is part of this long tradition of religiously motivated engineering. The social structure of the labor force that built the tunnel has been the subject of speculation by historians who have considered the possible sources of the workers who performed the heavy labor of rock cutting and rock removal. The workers may have been free citizens of Samos who were employed on the project as paid laborers, or they may have been slaves who were owned by Polycrates or by the Samian state, and who were compelled to work on the project. The ancient sources do not provide specific information about the composition of the labor force, but the comparison with other large-scale construction projects in the archaic Greek world suggests that a combination of free and slave labor was typically used, with free citizens performing the skilled work and slaves performing the unskilled heavy labor. The specific skills that the tunnel workers needed to possess included the ability to cut rock with iron tools, the ability to work in confined underground spaces, the ability to follow the directions of the supervising engineer, and the endurance to perform physically demanding labor for extended periods in difficult conditions. The development of these skills would have required a period of training and of acclimatization, and the tunnel workers who persisted throughout the construction would have become highly specialized in the techniques of tunnel excavation, developing an expertise that was valuable and that was not easily replaced. The specific question of how the tunnel entrances were determined, where exactly on each side of the mountain the digging should begin, is one that reveals the sophistication of the initial planning phase of the project. The south entrance of the tunnel had to be located at an elevation that was consistent with the delivery of water to the city, which was at a specific elevation above sea level, and the north entrance had to be located at an elevation that was consistent with the collection of water from the spring, which was at a higher elevation. The difference in elevation between the two entrances, which determined the overall slope of the tunnel and the rate at which the water would flow, had to be calculated in advance and had to be consistent with the hydraulic requirements of the water supply system. The selection of the specific entrance locations also had to take into account the geological conditions at each potential entrance site, because the rock type and the rock quality at the entrance would influence the stability of the tunnel opening and the ease with which the initial excavation could be conducted. The geological survey that Eupalinos would have conducted before the construction began would have identified the specific locations on each side of the mountain where the rock conditions were most favorable for the tunnel entrances, and the final selection of the entrance locations would have been the result of a compromise between the hydraulic requirements, the geological conditions, and the alignment constraints. The initial excavation of the tunnel at each entrance would have been the most critical phase of the construction, because the direction and the slope of the initial excavation determined the alignment of the entire tunnel. Any error in the direction or the slope of the initial excavation would have been propagated along the entire length of the tunnel, and the correction of such an error, once the excavation had proceeded beyond the first few meters, would have been difficult and costly. The specific care that Eupalinos took in establishing the initial alignment of the tunnel, using the sighting stakes and the leveling instruments that we have described, would have been critical for the success of the project. The question of whether the Samian engineering tradition continued after the fall of Polycrates is one that has been addressed by historians who have traced the subsequent history of the island. Polycrates was killed by the Persians in approximately 522 before the Common Era, and Samos was subsequently incorporated into the Persian Empire and later into the Athenian-led Delian League. The engineering capabilities that had been developed during Polycrates' reign, including the specific skills that had been used to build the tunnel, may have been transmitted to subsequent generations of Samian engineers, but the specific evidence for this transmission is limited, and the extent to which the Samian engineering tradition influenced the broader development of Greek engineering is uncertain. The core problem of the tunnel of Eupalinos is the alignment problem, the problem of ensuring that two tunnels dug from opposite sides of a mountain meet in the middle. This problem, which seems simple in its statement, is extraordinarily difficult in its execution, because the two tunnel teams are working underground, in the dark, separated by hundreds of meters of solid rock, with no direct line of sight and no direct means of communication. The alignment of the two tunnels requires that each team dig in precisely the correct direction, at precisely the correct slope, for precisely the correct distance, so that the two tunnels intersect at a predetermined point within the mountain. An error of a few degrees in the direction of either tunnel would cause the tunnels to miss each other entirely, and the entire project would fail. The magnitude of the alignment problem can be appreciated by considering the specific geometry of the tunnel of Eupalinos. The tunnel is approximately 1,036 meters long, and it passes through the mountain at a depth of approximately 160 meters below the summit. The two tunnel entrances are approximately 1 kilometer apart, separated by the bulk of Mount Kastro. The two teams of diggers could not see each other, could not hear each other through the rock, and had no electronic or optical means of maintaining contact. Each team had to dig in the direction that had been calculated before the work began, trusting that the calculations were correct and that the other team was digging in the complementary direction. The specific precision that was required for the alignment of the tunnel can be quantified. The two tunnels, each approximately 500 meters long, had to meet within a tolerance of a few meters in both the horizontal and the vertical dimensions. The horizontal alignment required that the direction of each tunnel be correct to, within approximately 1/5 of a degree, a precision that is impressive even by modern standards, and that would have required surveying measurements of exceptional accuracy. The vertical alignment required that the slope of each tunnel be controlled to within a few centimeters per 100 meters, a precision that required the use of a level or a water-based leveling device of considerable accuracy. But here is the problem. The standard interpretation of Greek surveying capability in the 6th century, before the Common Era, does not credit the Greeks with the ability to achieve this level of precision. The standard narrative of the history of surveying presents the development of precise surveying instruments and techniques as a gradual process that extended over many centuries, with the most precise instruments and techniques being developed only in the modern era. The Tunnel of Eupalinos challenges this narrative because it demonstrates that a level of surveying precision that was not supposed to be available in the 6th century before the Common Era was, in fact, achieved by a Greek engineer working on a Greek island in the Aegean Sea. The investigation of the Tunnel of Eupalinos has focused primarily on the question of how Eupalinos achieved the alignment, and several hypotheses have been proposed to explain the specific surveying technique that he used. The hypotheses differ in their assumptions about the mathematical knowledge and the surveying instruments that were available to Eupalinos, and they differ in their predictions about the specific path that the tunnel should follow if the proposed technique was used. The comparison of these predictions with the actual path of the tunnel, which has been surveyed with modern instruments, provides a means of evaluating the competing hypotheses and of determining which technique Eupalinos most likely used. The first hypothesis, which was proposed by the British historian of science B.L. van der Waerden in the 1950s, is that Eupalinos used a technique of triangulation to determine the relative positions of the two tunnel entrances and the direction in which each tunnel should be dug. The triangulation technique involves the measurement of the distances and the angles of a network of triangles that connect the two tunnel entrances across the surface of the mountain, and the calculation of the relative positions of the entrances from these measurements using the principles of plane geometry. The triangulation technique requires a knowledge of the Pythagorean theorem and of the basic principles of similar triangles, knowledge that was available in the Greek world by the 6th century before the Common Era. The second hypothesis, which was proposed by the German archaeologist Hermann Kienast, who conducted the most detailed modern survey of the tunnel in the 1980s and 90s, is that Eupalinos used a technique of zigzag survey lines to transfer the alignment from the surface of the mountain to the tunnel entrances. The zigzag technique involves the establishment of a series of straight survey lines that traverse the surface of the mountain from one tunnel entrance to the other, with each line changing direction at a measured angle. The total change in direction along the zigzag path, combined with the measured lengths of the individual segments, allows the surveyor to calculate the relative positions of the two endpoints and the direction from each endpoint to the other. The Kienast hypothesis has the advantage of being consistent with the specific features of the tunnel that have been revealed by the modern survey, including a distinctive change in direction in the middle section of the tunnel that is consistent with the correction that would have been needed if Eupalinos had used the zigzag technique and had discovered during the construction that the initial alignment needed adjustment. The change in direction, which occurs in the section of the tunnel that was dug from the north, is a sharp turn of approximately 15 degrees that redirects the tunnel toward the south team's heading, and it has been interpreted by Kienast as evidence that Eupalinos detected a misalignment during the construction and corrected it by changing the direction of the north tunnel. And it gets worse for anyone who assumes that ancient surveying was imprecise. The third hypothesis, proposed by the historian of ancient mathematics Tom Apostol and the mathematician Mamakon Natsakanian, suggests that Eupalinos may have used a method based on the establishment of two parallel lines running along opposite flanks of the mountain, connected by perpendicular offsets, creating a geometric framework that allowed the calculation of the tunnel direction from each side. This method, which relies on the principles of parallel lines and right angles that were well established in Greek geometry by the 6th century before the Common Era, could have provided the necessary alignment accuracy without requiring the measurement of long distances or the establishment of line-of-sight connections across the summit of the mountain. The evidence of the tunnel itself provides important constraints on the competing hypotheses. The modern survey of the tunnel, which was conducted by Kienast using electronic distance measurement and laser surveying equipment, has produced a detailed three-dimensional map of the tunnel's path that shows the specific course that each team of diggers followed. The map reveals that the south tunnel follows a relatively straight path for most of its length, while the north tunnel follows a more erratic path, with several changes in direction that suggest that the North team was less certain of its heading and that it made corrections during the construction. The specific pattern of the corrections in the North Tunnel is one of the most informative features of the tunnel's path because it provides evidence about the technique that was used to maintain the alignment. The corrections are not random. They follow a systematic pattern that suggests that the North team was making deliberate adjustments to its heading based on information that was obtained from the surface survey, possibly through the sinking of vertical probe holes or through the use of acoustic signals that were transmitted through the rock. The systematic nature of the corrections suggests that the alignment was not a one-time calculation that was made at the beginning of the construction, and that was then followed blindly by the diggers, but a continuous process of monitoring and adjustment that was maintained throughout the construction period. The meeting point of the two tunnels, which is the most dramatic moment in the story of the tunnel's construction, has been examined in detail by the modern surveyors. The two tunnels do not meet in a straight line. They meet at a slight angle, with the North Tunnel curving toward the east in its final meters and the South Tunnel curving toward the west, so that the two tunnels intersect at an angle of approximately 15 to 20 degrees rather than meeting head-on. The oblique intersection suggests that the two teams, as they approached the meeting point, could hear each other's work through the thinning rock, and that they adjusted their headings to ensure that the tunnels connected, even if the connection was not perfectly aligned. But here is what makes this truly terrifying. The oblique intersection of the two tunnels, which has been interpreted by some researchers as evidence that the alignment was less precise than the proponents of the triangulation hypothesis claim, is itself an impressive achievement because it demonstrates that the two teams were able to detect each other's proximity through the rock, to adjust their headings in response to this information, and to achieve a connection that was accurate to within less than 2 meters in the horizontal dimension and less than 1 meter in the vertical dimension. The meeting of the two tunnels, even if it was assisted by acoustic detection in the final meters, was the culmination of a surveying and engineering process that maintained the alignment to within a fraction of a degree over a distance of more than a kilometer through solid rock using only the instruments and the techniques that were available in the 6th century before the Common Era. The comparison between the Tunnel of Eupalinos and other ancient tunnels provides context for evaluating the achievement. The Hezekiah Tunnel in Jerusalem, which was built approximately 2 centuries before the Eupalinos Tunnel, in approximately 700 before the Common Era, is another ancient tunnel that was dug from both ends. The Hezekiah Tunnel, which is approximately 530 meters long, follows a sinuous S-shaped path that wanders considerably from the straight line between its two entrances, covering a distance that is nearly twice the straight line distance. The meandering path of the Hezekiah Tunnel has been interpreted as evidence that the builders did not have a precise surveying technique for aligning the two tunnel faces, and that they relied on a combination of acoustic detection and trial and error to achieve the connection. The contrast between the relatively straight path of the Eupalinos Tunnel and the meandering path of the Hezekiah Tunnel highlights the advance in surveying technique that the Eupalinos Tunnel represents and the specific contribution that Eupalinos' mathematical approach made to the success of the project. The specific mathematical knowledge that was available to Eupalinos in the 6th century before the Common Era is a crucial factor in the evaluation of the competing alignment hypotheses. The 6th century before the Common Era was a period of extraordinary mathematical activity in the Greek world, and the specific mathematical knowledge that was being developed during this period, including the Pythagorean theorem, the theory of similar triangles, and the basic principles of plane geometry, was directly relevant to the surveying techniques that Eupalinos would have needed to align the tunnel. The connection between the mathematical revolution of the 6th century and the engineering achievement of the Eupalinos tunnel is one of the most fascinating aspects of the tunnel's story, because it demonstrates that the abstract mathematical knowledge that was being developed by the Greek mathematicians was being applied in real time to the solution of practical engineering problems. The mathematician Pythagoras, who was born on the island of Samos, and who lived there during the early years of Polycrates' reign before moving to southern Italy, provides a direct connection between the mathematical tradition of the 6th century and the island on which the tunnel was built. The question of whether Pythagoras had any direct involvement with the design of the tunnel, or whether his mathematical discoveries were used by Eupalinos in the alignment calculations, is one that has been speculated about, but that cannot be confirmed from the available evidence. The coincidence that one of the greatest mathematicians of the ancient world and one of the greatest engineering projects of the ancient world were associated with the same island and the same period is suggestive but not conclusive, and the specific relationship between Pythagoras and the tunnel remains a matter of speculation. The specific question of how Eupalinos controlled the vertical alignment of the tunnel, ensuring that the two tunnels met at the same elevation, is distinct from the question of horizontal alignment and presents its own set of challenges. The vertical alignment of a tunnel requires the measurement of the elevation difference between the two tunnel entrances and the calculation of the slope at which each tunnel must be dug in order to meet at the correct elevation. The measurement of elevation differences over long distances across the surface of a mountain is a challenging task that requires the use of a precision leveling instrument, and that is subject to cumulative errors that can be significant over distances of a kilometre or more. The instrument that Eupalinos most likely used for the vertical alignment is the chorobates, a long, horizontal beam with a water trough on its upper surface that served as a level. The chorobates was placed on a series of supports at intervals along the survey line, and the level of the water in the trough was used to establish a horizontal reference plane from which the elevation of the ground could be measured. The accuracy of the chorobates depends on the length of the beam, the precision with which the water trough was manufactured, and the skill of the operator in reading the level. And the best estimates of the accuracy of the ancient chorobates suggest that it could establish horizontal levels with an accuracy of approximately 1 centimetre per 100 metres. The cumulative accuracy of the levelling over the full distance of the traverse around the mountain, which was approximately 2 to 3 kilometres, would have been in the range of 20 to 30 centimetres, consistent with the approximately 30 centimetre vertical error that is observed at the meeting point of the tunnel. The agreement between the estimated accuracy of the ancient levelling instrument and the observed vertical error at the meeting point provides strong support for the hypothesis that Eupalinos used the chorobates or a similar levelling instrument for the vertical alignment. The specific pattern of the vertical profile of the tunnel, which has been revealed by Kianast's survey, shows that the two halves of the tunnel are dug at slightly different slopes, with the south tunnel sloping downward toward the meeting point at a steeper angle than the north tunnel. The difference in the slopes may reflect a deliberate strategy by Eupalinos, who may have dug the two halves at slightly different slopes to ensure that the tunnels would meet in the vertical dimension. Even if the elevation measurements contained small errors, the strategy of dug at slightly different slopes would create a vertical funnel at the meeting point, increasing the probability that the two tunnels would intersect, even if the elevation calculations were slightly off. The evidence for this deliberate strategy is circumstantial but suggestive. The specific slope difference between the two halves of the tunnel is consistent with the error margin that would be expected from the use of the chorobates, and the direction of the slope difference, with the south tunnel steeper than the north tunnel, is the direction that would maximize the probability of intersection. The possibility that Eupalinos deliberately introduced a slope difference as a safety margin for the vertical alignment is consistent with the engineering judgment that would be expected of an experienced tunnel engineer and provides further evidence of the sophistication of his approach. The discovery, during the modern survey of the tunnel, that the tunnel deviates from a straight line in several specific ways that are consistent with deliberate course corrections rather than with random errors, has been one of the most important findings of the investigation. The course corrections, which are particularly evident in the North Tunnel, follow a pattern that suggests that the North team was receiving information about its position relative to the intended alignment, possibly through the use of vertical probe holes or through surface survey measurements that were communicated to the tunnel face through the tunnel entrance. The vertical probe holes, if they were used, would have been narrow shafts drilled from the surface of the mountain down to the level of the tunnel, providing a direct connection between the surface survey and the underground work. The probe holes would have served two purposes. They would have provided a means of checking the horizontal position of the tunnel face against the surface survey, and they would have provided a source of fresh air and light to the tunnel face. The archaeological evidence for the use of probe holes in the Eupalinos tunnel is limited, because any probe holes that were dug would have been filled in after the tunnel was completed, and the evidence of the filled holes has not been conclusively identified on the surface of the mountain. The specific methodology of the traverse survey that Eupalinos is believed to have used deserves detailed examination, because the technique is the foundation of the most widely accepted explanation for the tunnel's alignment. A traverse survey involves the measurement of a connected series of straight-line segments that form a path from one point to another, with the direction and the length of each segment being measured and recorded. The direction of each segment is measured relative to the previous segment, typically by measuring the angle between the two segments, and the cumulative effect of all the measured angles and lengths allows the surveyor to calculate the relative position of the endpoint of the traverse, the second tunnel entrance, relative to the starting point of the traverse, the first tunnel entrance. The key difficulty of the traverse survey is the accumulation of errors. Each measurement of angle and length contains a small error, and these errors accumulate as the traverse progresses, so that the final calculated position of the endpoint may differ from the true position by an amount that depends on the size of the individual errors and on the number of measurements in the traverse. The management of accumulated errors is the central challenge of traverse surveying, and the techniques that have been developed for managing these errors, including the use of redundant measurements, the use of closing errors to detect and correct mistakes, and the use of adjustment techniques to distribute the accumulated error evenly across the traverse, are among the most important contributions of the surveying profession to the practice of engineering. The specific error that is observed at the meeting point of the Eupalinos tunnel, approximately 60 centimeters in the horizontal dimension and approximately 30 centimeters in the vertical dimension, is consistent with the accumulated error that would be expected from a traverse survey of approximately 2 to 3 kilometers, using instruments with the accuracy of the ancient Groma and Chorobates and operated by a skilled surveyor. The consistency between the observed error and the predicted error provides strong support for the traverse survey hypothesis, and suggests that Eupalinos' surveying technique was well adapted to the specific requirements of the problem. The specific path of the traverse, which must have followed the surface of the mountain from one tunnel entrance to the other, has been reconstructed by several researchers who have walked the mountain and who have identified possible traverse routes that are consistent with the terrain and with the line-of-sight constraints that would have governed the choice of traverse stations. The most plausible traverse route follows the eastern flank of the mountain, where the terrain is relatively gentle, and where the line of sight from one traverse station to the next would have been unobstructed over distances of approximately 100 to 200 meters, the maximum distance over which the Groma could be used effectively. The specific question of how the tunnel face was maintained in the correct direction during the long, slow process of excavation deserves further analysis. The direction of the tunnel face, which had to be maintained to within approximately 1/5 of a degree over a distance of 500 meters, could not be checked directly against the surface survey, because the tunnel face was deep within the mountain and was accessible only through the tunnel itself. The maintenance of the correct direction required a method of transferring the surface alignment into the tunnel, and of checking the direction of the tunnel face against this transferred alignment at regular intervals. The most plausible method for transferring the alignment from the surface into the tunnel is the use of sighting stakes or sighting marks that were established at the tunnel entrance, and that defined the direction in which the tunnel should be dug. The sighting stakes, which would have consisted of vertical poles with marked reference points, would have been placed at the tunnel entrance in the alignment that had been calculated from the surface survey, and the tunnel diggers would have maintained the correct direction by sighting back along the tunnel from the working face to the entrance marks, and ensuring that the tunnel face was in line with the marks. The method of backsighting from the tunnel face to the entrance marks is effective for relatively short tunnels, where the entrance is visible from the working face, but it becomes increasingly difficult as the tunnel lengthens, because the distance between the working face and the entrance increases, and because the line of sight is obstructed by the curvature of the tunnel, by the dust in the air, and by the limited range of the oil lamps that provided the illumination. For a tunnel of the length of the Eupalinos tunnel, the back-sighting method would have been effective for the first few hundred meters, after which the entrance marks would have become invisible from the working face, and an alternative method of maintaining the alignment would have been needed. The alternative method that Eupalinos may have used to maintain the alignment in the deeper sections of the tunnel is the use of intermediate sighting marks that were established at intervals along the length of the tunnel and that defined the alignment of the tunnel at each interval. The intermediate marks, which would have been placed on the walls or on the ceiling of the tunnel at the correct alignment, would have provided a series of reference points that the diggers could use to maintain the correct direction as the tunnel advanced without the need to sight all the way back to the entrance. The establishment of the intermediate sighting marks would have required a skilled surveyor to work within the tunnel, using a sighting device, such as a groma or a simplified alignment instrument, to establish each new mark in line with the previous marks and with the calculated alignment of the tunnel. The accuracy of the intermediate marks would have depended on the accuracy of the sighting device and on the skill of the surveyor in aligning the marks, and any error in the placement of an intermediate mark would have been propagated to all subsequent marks, causing a progressive drift in the alignment of the tunnel. The specific pattern of the alignment deviations in the north tunnel of Eupalinos, which has been revealed by the modern survey, is consistent with the use of intermediate sighting marks that were periodically checked and corrected against the surface survey. The deviations show a pattern of gradual drift followed by abrupt correction, a pattern that is characteristic of a system in which the alignment is maintained by internal reference marks that gradually accumulate errors and that are periodically corrected by reference to an external standard. The specific question of the horizontal alignment method is one that has generated the most detailed mathematical analysis of any aspect of the tunnel's construction. The mathematical analysis has focused on the determination of the direction from each tunnel entrance to the meeting point within the mountain, a calculation that requires the determination of the relative positions of the two tunnel entrances in a common coordinate system. The determination of the relative positions of the two tunnel entrances can be accomplished by several different surveying methods, each of which has its own advantages and its own sources of error. The most direct method, which involves the establishment of a line of sight between the two entrances, is not possible for the Eupalinos tunnel because the mountain blocks the line of sight. The alternative methods, which involve the measurement of distances and angles along a survey traverse that goes over or around the mountain, are all indirect methods that require the calculation of the relative positions from the measured data. The mathematical operation that is required to convert the traverse measurements into the relative positions of the two endpoints is a coordinate transformation, a calculation that involves the conversion of the measured distances and angles into the north-south and east-west components of each traverse segment, and the summation of these components to determining the total displacement from one endpoint to the other. The coordinate transformation is a standard operation in modern surveying, and it requires a knowledge of trigonometry, the mathematical technique for calculating the sides and the angles of triangles from known information about some of the sides and some of the angles. The question of whether Eupalinos had access to trigonometric calculations, which are not documented in the Greek mathematical literature until the work of Hipparchus in the 2nd century before the Common Era, approximately 3 centuries after the construction of the tunnel, has been a subject of debate among historians of mathematics. The resolution of this debate has significant implications for the evaluation of the alignment hypotheses, because the methods that Eupalinos could have used for the alignment calculation depend on the mathematical tools that were available to him. The consensus among historians of mathematics is that Eupalinos did not have access to trigonometric calculations in the formal sense, but that he could have performed the equivalent calculations using the properties of similar triangles and the Pythagorean theorem, both of which were known in the Greek mathematical tradition by the 6th century before the Common Era. The use of similar triangles to solve problems that involve the calculation of unknown distances and angles from known ones is a technique that is equivalent in its results to the use of trigonometry, though it is less systematic and less general. The Pythagorean theorem, which provides the relationship between the sides of a right triangle, is the specific mathematical result that would have been most useful for the conversion of traverse measurements into coordinates, and its availability in the 6th century provides a plausible mathematical foundation for the alignment calculations. The specific computation that Eupalinos would have needed to perform can be illustrated with a simplified example. Imagine a traverse consisting of 3 segments that run from the south tunnel entrance to the north tunnel entrance. The surveyor measures the length and the direction of each segment, and he needs to calculate the total displacement in both the north-south and the east-west directions from one entrance to the other. Using the properties of similar triangles or the Pythagorean theorem, the surveyor can decompose each segment into its north-south and east-west components, and then sum the components to determine the total displacement. The direction from each entrance to the meeting point can then be calculated from the total displacement, using the same geometric principles. The accuracy of this calculation depends on the accuracy of the individual length and angle measurements, and on the number of segments in the traverse. The error in each individual measurement accumulates as the traverse progresses, and the final error depends on both the individual measurement errors and on the geometry of the traverse, with traverses that involve more segments and more changes in direction accumulating more error than traverses that are shorter and straighter. The detailed investigation of the meeting zone, the specific section of the tunnel where the 2 excavations converge, has provided the most detailed and the most dramatic evidence of the construction process. The meeting zone, which extends for approximately 30 meters, shows a complex pattern of changes in direction, changes in elevation, and changes in cross-section that reflects the adjustments that the 2 teams made as they approached each other and as they detected each other's presence through the rock. The south tunnel, as it approaches the meeting zone, maintains a relatively straight path, with only minor deviations from the calculated alignment. The north tunnel, by contrast, shows a significant change in direction in the final 100 meters before the meeting zone, with the heading shifting from a southwesterly direction to a more southerly direction that brings the tunnel into alignment with the south team's heading. The change in direction in the north tunnel has been interpreted by Kianast as evidence of a deliberate course correction that was made when the north team realized, either through acoustic detection or through a surface survey check, that its heading was slightly off the intended alignment. The specific geometry of the meeting zone, in which the 2 tunnels approach each other at an oblique angle and connect through a short curved section of tunnel, suggests that the final connection was made by the south team, which appears to have extended its tunnel slightly to the east to meet the north tunnel at a point where the 2 headings converged. The curvature of the connecting section is smooth and deliberate, suggesting that the final connection was not a random discovery, but a controlled operation in which the south team adjusted its heading to intercept the approaching North Tunnel. The moment of the final connection, when the last thin partition of rock between the two tunnels was broken through and the two passages were joined into a single, continuous tunnel, would have been one of the most dramatic moments in the history of the project. The workers and the engineers who were present at the moment would have experienced the sudden rush of air through the opening, the sound of voices and of tools from the other side, and the light of oil lamps penetrating through the darkness from the opposite direction. The moment would have been both a physical sensation and an emotional experience, a confirmation that the years of labour and the mathematics of the alignment had been justified by the result. The investigation of the specific tools that were used in the final meters of the tunnel, as revealed by the tool marks on the rock face in the meeting zone, has shown that the tools used in the meeting zone are different from the tools used in the main body of the tunnel. The tool marks in the meeting zone are finer and more closely spaced than the marks in the main body, suggesting that the workers used smaller, more precise tools for the final approach, possibly to minimize the risk of overcutting and to maintain maximum control over the direction of the excavation. The use of smaller tools in the final approach is consistent with the hypothesis that the workers were aware of the proximity of the other team and that they were exercising extra care to ensure that the connection was made safely and accurately. The investigation of the specific features of the rock face at the tunnel walls has revealed evidence of the systematic approach that the ancient engineers used to maintain the direction of the excavation. At several points along the tunnel, small niches or recesses have been cut into the tunnel walls at regular intervals, and these niches have been interpreted by researchers as the locations where the sighting marks or the alignment instruments were placed during the construction. The regular spacing of the niches, which is approximately 20 to 30 meters, is consistent with the hypothesis that the alignment was checked at regular intervals using intermediate sighting marks, and the specific positions of the niches on the tunnel walls are consistent with the use of a sighting device that was mounted in the niches and that was used to establish the direction of the tunnel face. The investigation of the specific features of the tunnel at the point where the two excavations meet has also revealed evidence of the emotional and the ceremonial significance that the ancient workers attached to the moment of connection. The meeting point is marked by a widening of the tunnel that creates a small chamber at the junction of the two headings, and this chamber has been interpreted by some researchers as a deliberate expansion that was created to celebrate the meeting of the two teams and to provide a space for the ceremonial marking of the occasion. The ancient Greek tradition of dedicating engineering achievements to the gods through the inscription of dedicatory texts and the placement of votive offerings at significant locations suggests that the meeting point may have been the site of a dedicatory ceremony that marked the successful completion of the alignment. The dedication inscription that was found in the tunnel, which names Eupalinos of Megara as the designer of the tunnel, is one of the most important textual sources for the study of the tunnel and for the identification of the engineer who designed it. The inscription, which was carved on the rock face of the tunnel, at a location that has been identified by the modern surveyors, provides direct evidence that the tunnel was designed by a specific individual, Eupalinos, who was recognized by his contemporaries as the author of the engineering achievement. The inscription is one of the earliest known examples of the attribution of an engineering achievement to a specific individual, and it provides valuable evidence for the social status and the professional recognition of engineers in the archaic Greek world. The question of whether the inscription was placed by Eupalinos himself, by the workers who built the tunnel, or by Polycrates or his representatives is one that cannot be answered from the available evidence. The placement of the inscription within the tunnel, rather than on the exterior of the tunnel or on a public monument, suggests that the inscription was intended for a restricted audience, possibly the engineers and the workers who would maintain the tunnel in the future, rather than for the general public. The restricted placement of the inscription is consistent with the hypothesis that the inscription was a technical record rather than a public advertisement, a record that identified the designer of the tunnel for the benefit of future engineers who might need to understand the design in order to maintain or to modify the tunnel. The 13th major track of investigation concerns the broader significance of the tunnel for the understanding of ancient Greek attitudes toward technology and toward the relationship between intellectual achievement and practical accomplishment. The tunnel demonstrates that the ancient Greeks valued practical engineering achievement as well as theoretical intellectual achievement, and that the specific accomplishment of a tunnel that connected two sides of a mountain was regarded by Herodotus, and presumably by his contemporaries, as one of the greatest works of the Greek world. The specific language that Herodotus used to describe the tunnel, which he called one of the three greatest works accomplished by any Greeks, is significant because it places the tunnel in the same category as the Temple of Hera and the Harbour Mole, both of which were monumental works that were visible from the sea and that served as symbols of the power and the prosperity of the Samian state. The inclusion of the tunnel, which was invisible and which was accessible only through its two entrances, in the same category as these visible monuments, suggests that Herodotus valued the tunnel not for its visual impact, but for its engineering achievement, for the specific feat of surveying and of excavation that its construction represented. The recognition of the tunnel as one of the greatest works of the Greek world by the most important historian of the ancient world provides powerful evidence for the value that the ancient Greeks placed on engineering achievement and for the specific prestige that was accorded to the engineers who produced it. The recognition challenges the stereotype of the ancient Greeks as abstract thinkers who disdained practical activity, and it provides evidence for a more nuanced understanding of the Greek attitude toward technology, one that recognized and celebrated the specific achievements of the engineers alongside the more commonly celebrated achievements of the philosophers, the poets, and the politicians. The tunnel also provides evidence for the existence of a professional engineering class in the archaic Greek world, a class of individuals who possessed specific technical knowledge and who were hired by rulers and by cities to design and to execute specific engineering projects. The fact that Eupalinos was brought from Megara to Samos to design the tunnel suggests that the engineering profession was organized on a pan-Hellenic basis, with specific engineers being known for their specific expertise and being hired by patrons from across the Greek world. The existence of a professional engineering class in the archaic period is a significant finding because it challenges the assumption that the engineering profession did not develop in the Greek world until the Hellenistic period, and that the archaic engineers were merely craftsmen without professional standing. The question of whether Eupalinos trained apprentices who continued his engineering tradition after his death is one that cannot be answered from the available evidence, but the continued development of tunnel engineering in the subsequent centuries of Greek and Roman history suggests that the knowledge that Eupalinos accumulated during the construction of the Samos tunnel was, in some form, transmitted to subsequent generations of engineers. The investigation of the tunnel of Eupalinos has been conducted by archaeologists, engineers, surveyors, historians of mathematics, and classicists over a period of more than a century, and it has produced a body of research that is among the most detailed and most sophisticated in the history of ancient engineering studies. The investigation has proceeded along several major tracks, each of which has contributed to the understanding of the tunnel, and each of which has raised new questions about the specific methods that Eupalinos used to achieve his extraordinary feat. The first major track of investigation has been the archaeological excavation and the detailed survey of the tunnel itself. The tunnel was rediscovered in the late 19th century by archaeologists who were conducting excavations on Samos, and it has been the subject of increasingly detailed surveys over the following decades. The most comprehensive survey was conducted by Hermann Kienast of the German Archaeological Institute in Athens, who spent more than a decade surveying the tunnel with modern electronic instruments, and who published his results in a monumental study that remains the definitive reference work on the tunnels Geometry and construction. Kearney's survey revealed the precise three-dimensional path of the tunnel, including the deviations from the straight line, the changes in direction, the variations in cross-section, and the specific features of the rock face that provide evidence of the construction methods. The survey confirmed that the tunnel was dug from both ends simultaneously, as Herodotus had described, and it revealed the specific pattern of the two tunnels' paths, including the relatively straight path of the south tunnel and the more erratic path of the north tunnel. That provides evidence about the surveying techniques that were used. The numbers are striking when we consider the specific measurements that Kearney's survey produced. The total length of the tunnel is 1,036 meters. The horizontal alignment error at the meeting point is approximately 60 centimeters. The vertical alignment error at the meeting point is approximately 30 centimeters. The maximum depth of the tunnel below the surface of the mountain is approximately 170 meters. The cross-section of the tunnel is approximately 1.8 meters high by 1.8 meters wide for most of its length. The volume of rock that was removed during the construction is approximately 7,000 cubic meters, which at an estimated rate of 1 to 2 cubic meters per day per team would have required approximately 5 to 8 years of continuous work. The second major track of investigation has been the analysis of the construction techniques that were used to dig the tunnel, including the rock-cutting tools, the methods of rock removal, the techniques of ventilation and lighting, and the methods of surveying that were used to maintain the alignment during the construction. The analysis of the construction techniques has been based on the physical evidence of the tunnel itself, including the tool marks on the rock face, the patterns of the excavation, the evidence of ventilation and lighting, and the specific features of the tunnel's geometry that indicate the methods that were used. The tool marks on the rock face of the tunnel provide direct evidence of the tools and the techniques that were used to cut the rock. The marks are consistent with the use of iron picks and chisels, applied with a combination of direct percussion and indirect percussion, in which the chisel is struck with a hammer. The pattern of the tool marks indicates that the rock was cut in horizontal layers, with each layer being removed from top to bottom across the full width of the tunnel face, a technique that is efficient for the type of limestone through which the tunnel was dug, and that minimizes the risk of rock collapse. The water channel that runs along the floor of the tunnel is a separate construction from the tunnel itself and was built after the main tunnel was completed. The water channel, which is approximately 60 centimeters wide and approximately 1 meter deep, is cut into the floor of the tunnel and is lined with clay pipes that carry the water from the spring on the north side of the mountain to the city on the south side. The slope of the water channel, which is approximately 4 centimeters per 100 meters, is strikingly uniform, indicating that the builders achieved a level of accuracy in establishing the gradient that is consistent with the use of a precision leveling instrument. The third major track of investigation has been the mathematical analysis of the surveying techniques that Eupalinos may have used to achieve the alignment of the tunnel, aimed at determining which technique best explains the specific features of the tunnel's path and the specific errors that are observed in the alignment. The mathematical analysis has been conducted by historians of mathematics who have expertise in the mathematical knowledge that was available in the 6th century before the Common Era, and by surveyors who have expertise in the practical techniques of tunnel alignment. The analysis of the alignment method has focused on 3 critical questions: how Eupalinos determined the relative positions of the 2 tunnel entrances, how he calculated the direction in which each tunnel should be dug, and how he maintained the alignment during the construction when the diggers were deep within the mountain and could not see the surface. The first question, the determination of the relative positions of the 2 tunnel entrances, is the most fundamental because the accuracy of the entire alignment depends on the accuracy of this initial measurement. The 2 tunnel entrances are separated by the mountain, and there is no direct line of sight between them, which means that the relative position must be determined by indirect measurement, using a survey traverse that goes over or around the mountain. The specific method that Eupalinos used for this measurement is the primary subject of the competing hypotheses that we have described. The most widely accepted hypothesis, based on Kianast's analysis, is that Eupalinos used a traverse survey around the mountain, establishing a series of connected survey lines that ran from one tunnel entrance to the other along a path that followed the contour of the mountain. The traverse would have involved the measurement of the distance and the direction of each segment of the path, using a combination of distance measurement, which was accomplished by pacing or by the use of a measuring rod, and angle measurement, which was accomplished using a sighting device such as the groma. The accuracy of the traverse survey depends on the accuracy of the individual distance and angle measurements, and on the number of segments in the traverse. The longer the traverse and the greater the number of segments, the greater the opportunity for errors to accumulate, and the less accurate the final result. The traverse from one tunnel entrance to the other around the mountain would have been approximately 2 to 3 kilometers long, involving perhaps 15 to 20 individual segments, and the accumulated error over this distance would have been consistent with the 60 centimeter horizontal error that is observed at the meeting point. The fourth major track of investigation has been the experimental replication of the surveying techniques that Eupalinos may have used, aimed at testing whether the proposed techniques could achieve the level of accuracy that is observed in the tunnel. Several research groups have conducted experimental replications of the traverse survey using replicas of ancient surveying instruments, including the groma and the chorobates, and they have measured the accuracy that can be achieved with these instruments under field conditions. The results of the experimental replications have shown that the proposed surveying techniques are capable of achieving the level of accuracy that is observed in the tunnel of Eupalinos, provided that the measurements are made with care and that the instruments are used by skilled operators. The groma, which is a simple sighting device consisting of a vertical pole with two horizontal crossarms from which plumb lines are suspended, can establish right angles with an accuracy of approximately 1/10 of a degree, and the chorobates, which is a long, level beam with a water trough on top, can establish horizontal levels with an accuracy of approximately 1 centimeter per 100 meters. These levels of accuracy are consistent with the accuracy that is observed in the tunnel and support the hypothesis that the proposed surveying techniques were used. The fifth major track of investigation has been the study of the water supply system, of which the tunnel was a part, aimed at understanding the complete engineering system that delivered water from the spring to the city. The water supply system included not only the tunnel, but also an above-ground aqueduct on the north side of the mountain that collected the water from the spring and delivered it to the north entrance of the tunnel, the water channel within the tunnel that carried the water through the mountain, and a distribution system on the south side of the mountain that delivered the water to the city. The engineering of the complete water supply system demonstrates a sophisticated understanding of hydraulic principles, including the relationship between the slope of the channel, the flow rate of the water, and the capacity of the system. The sixth major track of investigation has been the study of the historical and the cultural context of the tunnel, aimed at understanding the specific conditions that made the construction of the tunnel possible and that determined the specific form that it took. The cultural context includes the intellectual tradition of Greek mathematics and geometry that provided the mathematical knowledge that was needed for the surveying, the political context of Polycrates' tyranny that provided the authority and the resources that were needed for the construction, and the military context of the threats that Samos faced from the Persian Empire and from rival Greek states that motivated the decision to build a tunnel rather than a surface aqueduct. The political dimension of the tunnel's construction deserves particular emphasis because the tunnel was as much a political statement as it was an engineering project. The construction of a tunnel through a mountain, using the most advanced surveying techniques available, was a demonstration of the power and the sophistication of Polycrates' regime and the completion of the tunnel was a source of prestige that enhanced the reputation of Samos across the Greek world. The association of the tunnel with the name of Eupalinos, rather than with the name of Polycrates, suggests that the engineering achievement was recognized as being the contribution of the engineer rather than of the ruler, a recognition that is unusual in the ancient world, where the credit for public works was typically attributed to the ruler who commissioned them rather than to the engineer who designed them. The seventh major track of investigation has been the comparative study of the tunnel of Eupalinos with other ancient tunnels and aqueducts, aimed at placing the tunnel in the broader context of ancient engineering and at evaluating its specific achievements against the achievements of other ancient builders. The comparison with the Hezekiah tunnel, which we have already mentioned, reveals the advance in surveying technique that the Eupalinos tunnel represents. The comparison with the Roman aqueducts, which were built several centuries after the Eupalinos tunnel, and which used more advanced surveying instruments and techniques, reveals that the Roman engineers achieved levels of accuracy that were comparable to those of the Eupalinos tunnel, but that they did so using longer tunnels and more complex routes. The qanat systems of the ancient Near East, which are underground water channels that were dug from the surface through a series of vertical shafts, and that use the natural slope of the ground to carry the water by gravity, provide another relevant comparison. The qanats, which were developed in the Iranian Plateau in the first millennium before the Common Era, and which were subsequently adopted across the ancient Near East and into North Africa and Spain, demonstrate a sophisticated understanding of underground hydraulic engineering that is comparable in some respects to the understanding demonstrated by the Eupalinos tunnel. The principal difference between the qanat system and the Eupalinos tunnel is the method of construction. The qanats are dug from the surface downward through vertical shafts, while the Eupalinos tunnel is dug horizontally from two entrances, a difference that requires a fundamentally different approach to the alignment problem. The preservation of the tunnel of Eupalinos over the past 25 centuries is itself a remarkable achievement, because the tunnel has survived earthquakes, geological changes, the rise and the fall of civilizations, and the neglect and the vandalism that have damaged many other ancient monuments. The tunnel was in use as an aqueduct for several centuries after its construction, and it was subsequently abandoned as the water supply needs of the city changed. The tunnel was rediscovered in the 19th century by archaeologists who were working on Samos, and it has been the subject of ongoing conservation and research since then. The modern conservation of the tunnel has included the stabilization of sections of the tunnel that were at risk of collapse, the installation of lighting and walkways to allow visitor access, and the documentation of the tunnel's condition using photographic, laser scanning, and other recording methods. The tunnel was inscribed on the UNESCO World Heritage List in 1992, along with the Heraion Temple and the ancient city of Pythagorean, as part of the archaeological site of Pythagorean and Heraion of Samos, recognizing the tunnel as one of the most important engineering achievements of the ancient world. The eighth major track of investigation has been the analysis of the labor organization that was required for the construction of the tunnel. The construction of a kilometer-long tunnel through solid rock was a massive labor undertaking that required the coordination of multiple teams of workers over a period of several years. The specific organization of the labor force, including the number of workers, the division of labor, the working hours, and the management of the supply chain for tools, food, water, and lighting materials, has been inferred from the physical evidence of the tunnel and from the comparison with other ancient construction projects. The estimated number of workers who were employed on the tunnel at any one time has been calculated based on the cross-section of the tunnel, which was large enough for only 2 or 3 workers to operate at the tunnel face simultaneously, and on the estimated rate of advance, which was approximately 1 to 2 meters per month. The calculation suggests that each tunnel employed a small team of workers at the face, perhaps 3 to 5 cutters who worked in shifts, supported by a larger team of workers who carried the excavated rock from the face to the entrance, maintained the tools, operated the ventilation and lighting systems, and managed the supply chain. The total labor force for each tunnel may have been approximately 20 to 30 workers, and the total labor force for the entire project, including both tunnels and the surface survey team, may have been approximately 50 to 70 workers. The cost of the labor, which was probably paid in the form of food, housing, and a daily wage in silver coins, would have been a significant proportion of the total cost of the project. The ancient sources do not provide specific information about the wages paid to the tunnel workers on Samos, but the comparison with other ancient construction projects suggests that the daily wage of a skilled worker in the 6th century, before the Common Era, was approximately 1 to 2 obols, a silver coin that was worth approximately 1/6 to 1/3 of a drachma. The total labor cost of the tunnel, based on the estimated number of workers and the estimate duration of the construction, would have been approximately 10 to 20 talents of silver, a significant sum that would have represented a substantial investment by Polycrates' treasury. The management of the excavated rock was a logistical challenge that required the continuous removal of large quantities of stone from the tunnel face to the surface. The rock was carried by hand in baskets or on wooden boards, passed from worker to worker along the length of the tunnel, and deposited on a spoil heap near the tunnel entrance. The spoil heaps from the construction of the Eupalinos tunnel have been identified by archaeologists on both sides of the mountain, and their volumes are consistent with the estimated volume of rock that was removed during the construction. The investigation of similar ancient tunnel projects from other cultures provides valuable comparative context for understanding the specific achievements and the specific limitations of the Eupalinos tunnel. The Roman tunnel of Claudius at Lake Fucino, which was built in the 1st century of the Common Era, and which was approximately 5.5 kilometers long, is one of the longest tunnels in the ancient world, and demonstrates the scale of the tunnel engineering that the Roman Empire was capable of achieving. The Claudius tunnel, which was designed to drain Lake Fucino in central Italy, was dug from multiple shafts along its length, a technique that allowed multiple teams to work simultaneously and that reduced the alignment problem to a series of shorter connections between adjacent shafts. The comparison between the Eupalinos tunnel and the Claudius tunnel reveals the specific advantages and the specific limitations of the two different approaches to tunnel construction. The shaft-based approach of the Claudius tunnel, which uses vertical shafts to divide the tunnel into shorter segments, reduces the alignment problem but requires the excavation of the shafts themselves, which is a costly and a time-consuming process, particularly in deep tunnels where the shafts may be hundreds of meters deep. The two-entrance approach of the Eupalinos tunnel, which relies on a single continuous survey from one entrance to the other, avoids the cost of the shafts but requires a much more precise survey because the error accumulates over the full length of the tunnel rather than being limited to the length of each individual segment. The Persian Qanat systems, which we have already mentioned, provide another relevant comparison. The Qanats, which are among the most extensive and most sophisticated underground hydraulic systems in the ancient world, demonstrate a level of expertise in underground water engineering that is comparable to the expertise demonstrated by the Eupalinos tunnel. The Qanat builders, who worked in the arid regions of the Iranian plateau and of Central Asia, developed techniques for the location of underground water, for the design of underground channels with controlled gradients, and for the maintenance and the repair of underground systems that were highly specialized and that were transmitted through a specific guild tradition over many generations. The comparison with the mining tunnels of the ancient world, including the silver mines of Laurion in Greece and the gold mines of Spain and of Wales, provides additional context for the evaluation of the Eupalinos tunnel. The ancient miners developed techniques for the excavation of rock, for the ventilation and the lighting of underground workspaces, and for the management of water that were directly relevant to the construction of tunnels and aqueducts. The specific techniques of the ancient miners, including the use of fire setting, in which the rock face was heated by a fire and then cooled rapidly with water to cause it to crack and to spall, may have been used in the construction of the Eupalinos tunnel, though the archaeological evidence for fire setting in the tunnel is limited. The ninth major track of investigation has been the analysis of the environmental conditions within the tunnel during and after its construction, including the temperature, the humidity, the airflow patterns, and the geological stability of the rock. The analysis of these conditions has been conducted through direct measurement and through comparison with other underground environments of similar depth and similar geological composition. The temperature within the tunnel is approximately 17 to 18 degrees Celsius throughout the year, a temperature that is determined by the average annual surface temperature of the area, and that is effectively constant, without the seasonal variations that characterize the surface temperature. The constant temperature of the tunnel, which would have been the same during the construction as it is today, would have provided a comfortable working environment for the tunnel workers who would not have been subjected to the extreme heat of the Samian summer or the occasional cold of the Samian winter. The humidity within the tunnel is high, typically close to saturation, because the rock through which the tunnel is dug is a porous limestone that contains moisture, and the moisture evaporates from the rock surfaces into the tunnel air, maintaining a high level of humidity. The high humidity would have been a challenge for the tunnel workers during the construction, because the humid air, combined with the dust that was generated by the rock cutting, would have created difficult breathing conditions, particularly at the tunnel face, where the ventilation was poorest. The geological stability of the tunnel, which has been maintained for over 2,500 years, is a consequence of the specific properties of the limestone through which the tunnel was dug. The limestone of Mount Kastro is a relatively uniform, moderately strong rock that is resistant to collapse and that maintains its structural integrity without the need for lining or for support structures. The tunnel was dug without the use of any lining or support over most of its length, and the fact that the tunnel has survived for 2,500 years without significant collapse is evidence of the quality of the rock and of the skill of the builders in selecting a tunnel route that avoided the zones of weak or fractured rock. The investigation of the specific sections of the tunnel where the rock quality is poorer and where the tunnel shows evidence of partial collapse or of remedial support work has provided information about the geological conditions that were encountered during the construction and about the techniques that were used to deal with unstable rock. The sections of poor rock quality, which are typically associated with geological faults or with zones of intense weathering, were stabilized by the ancient builders using dry stone masonry that was built up from the floor to form arched supports that distributed the weight of the overlying rock. The dry stone supports, which are still in place and which are still performing their structural function after 25 centuries, demonstrate the skill of the ancient builders in dealing with difficult geological conditions. The 10th major track of investigation has been the study of the acoustic properties of the tunnel, aimed at determining whether the two tunnel teams could hear each other through the rock and at evaluating the role of acoustic detection in the final phase of the tunnel's construction. The acoustic properties of limestone, which is the rock through which the tunnel was dug, are well characterized by modern physics, and the speed of sound through limestone is approximately 3,000 to 6,000 meters per second, depending on the density and the porosity of the rock. The transmission of sound through the rock would have allowed the two tunnel teams to hear each other's work when the intervening rock had thinned to a thickness of approximately 10 to 30 meters, depending on the loudness of the sound and the sensitivity of the listeners. The detection of the other team's work through the rock would have been a dramatic and a profoundly reassuring moment for the tunnel workers, who had been digging for years in the dark, trusting the calculations of an engineer they could not see, and heading toward a meeting point that they could not verify. The first faint sounds of the other team's picks through the rock would have confirmed that the alignment was correct, that the two tunnels were approaching each other, and that the meeting was imminent. The evidence of the tunnel itself, which shows that the two tunnels change direction slightly in their final meters, curving toward each other and meeting at an oblique angle, is consistent with the hypothesis that the final approach was guided by acoustic detection rather than by the survey alignment. The use of acoustic detection to guide the final approach of the two tunnels is not merely a plausible hypothesis. It is a technique that has been used in tunnel construction throughout history, from the ancient world to the modern era, and it is one of the simplest and most reliable methods for achieving the final connection between two tunnels that have been dug from opposite directions. The technique requires no instruments and no calculations. It requires only the ability to hear and the direction from which the sound of the other team's work is coming. Provides an immediate and a reliable indication of the direction in which the tunnel should be dug to achieve the connection. The 11th major track of investigation has been the detailed three-dimensional laser scanning of the tunnel, which has been conducted in recent years using modern laser scanning technology that was not available to the earlier researchers. The laser scanning, which produces a dense cloud of three-dimensional points that represents the surfaces of the tunnel walls, ceiling, and floor with millimeter-level precision, has provided a comprehensive digital model of the tunnel that can be analysed using computer software to determine the precise geometry of the tunnel's path. The laser scanning data has confirmed and refined the earlier measurements that were conducted by Kianast using electronic distance measurement, and it has revealed additional details of the tunnel's geometry that were not apparent in the earlier data. The specific details that the laser scanning has revealed include the precise cross-sectional shape of the tunnel at each point along its length, the precise position and the precise dimensions of the tool marks on the rock face, the precise geometry of the water channel on the tunnel floor, and the precise three-dimensional coordinates of the meeting point where the two tunnels connect. The laser scanning data has also been used to create a virtual reality model of the tunnel that allows researchers and the public to explore the tunnel's interior in 3 dimensions on a computer screen. The virtual reality model, which reproduces the geometry and the surface texture of the tunnel with photographic realism, provides an immersive experience that conveys the scale and the character of the tunnel in a way that photographs and drawings cannot. The virtual reality model has been used for educational purposes, allowing students and the general public to explore the tunnel and to understand the engineering challenges that Eupalinos faced. Without the need to travel to Samos, the creation of the digital model has also facilitated the analysis of the construction sequence of the tunnel because the three-dimensional data allows researchers to identify the specific features of the tunnel's geometry that correspond to specific stages of the construction process. The identification of the construction stages, which include the initial excavation, the alignment corrections, the final approach, and the post-construction modifications, provides a detailed chronological narrative of the tunnel's construction that can be compared with the historical evidence to produce a comprehensive account of the project. The digital preservation of the tunnel through laser scanning and through the creation of the virtual reality model is also important for the long-term conservation of the tunnel because the digital data provides a permanent record of the tunnel's current condition that can be used to monitor changes over time and to detect any deterioration that might threaten the tunnel's structural integrity. The digital record, which can be stored indefinitely and which can be accessed by researchers anywhere in the world, provides a form of preservation that is complementary to the physical preservation of the tunnel itself, and that ensures that the information contained in the tunnel will be available to future generations even if the physical tunnel is damaged or destroyed. The 12th major track of investigation has been the study of the economic impact of the tunnel on the city of Pythagorean and on the island of Samos as a whole. The tunnel, by providing a secure and reliable water supply to the city, would have enhanced the city's ability to sustain a large population, to support commercial and industrial activity, and to withstand the sieges and the blockades that were a constant threat in the military environment of the archaic Greek world. The economic benefits of the tunnel, which included the increased agricultural productivity that the water supply enabled, the increased commercial activity that the secure water supply attracted, and the military security that the protected water supply provided would have been substantial and would have justified the enormous investment that the construction of the tunnel required. The comparison between the cost of the tunnel and the cost of the alternative, a surface aqueduct that would have been vulnerable to attack, provides an economic analysis of the decision to build the tunnel. The tunnel would have been significantly more expensive than a surface aqueduct, because the excavation of rock is far more costly than the construction of an above-ground channel. But the tunnel would also have been far more secure, because the underground route was invisible and inaccessible to an attacker, while a surface aqueduct could have been easily discovered and destroyed. The additional cost of the tunnel, relative to the surface aqueduct, was therefore the cost of the military security that the tunnel provided, an insurance premium that Polycrates judged to be justified by the specific military threats that Samos faced. The long-term economic impact of the tunnel, which remained in use for several centuries after its construction, would have been measured not only in the direct benefits of the water supply, but also in the indirect benefits of the engineering knowledge and the institutional capacity that the construction of the tunnel developed. The construction of the tunnel required the development of specific engineering skills, specific organizational capabilities, and specific institutional structures that were valuable for other construction projects, and that contributed to the broader engineering capability of the Samian community. The tunnel, in this sense, was not only a water supply project, but also an investment in the human capital and the institutional capacity of the Samian state. The investigation of the post-construction history of the tunnel has revealed that the tunnel was modified and maintained at various times during its centuries of use, with repairs to sections of the tunnel that were damaged by geological movement or by the deterioration of the rock, and with modifications to the water channel to accommodate changes in the water supply requirements of the city. The evidence of these modifications, which includes patches of masonry that differ in style from the original construction and sections of the water channel that have been rebuilt or redirected, provides information about the engineering practices of the periods in which the modifications were made, and about the changing needs of the community that the tunnel served. The abandonment of the tunnel, which occurred at some point during the late antique or the early medieval period, was probably the result of changes in the water supply requirements of the community, including the decline of the population of Pythagorean and the development of alternative water sources that made the tunnel unnecessary. The abandoned tunnel, which was no longer maintained and which was gradually forgotten by the local community, survived as a silent passage through the mountain, its walls still standing, its alignment still accurate, its engineering still impressive, waiting to be rediscovered by the archaeologists of the modern era and to take its rightful place among the greatest engineering achievements of the ancient world. The investigation of the specific techniques that were used by the tunnel workers to manage the stress and the psychological challenges of working underground for extended periods is one that has been explored by researchers who have drawn on the evidence of the tunnel itself and on the comparison with other ancient and modern underground construction projects. The underground work environment, with its darkness, its confinement, its dust, and its isolation from the surface world, would have imposed significant psychological challenges on the workers, and the management of these challenges would have been an important aspect of the project's organization. The specific conditions at the tunnel face, where the rock was being cut and where the air quality was at its worst, would have been the most challenging for the workers. The tunnel face was the most confined space in the tunnel, with room for only 2 or 3 workers to operate simultaneously, and the dust generated by the rock cutting would have reduced the visibility and the air quality to levels that would have been dangerous without some form of ventilation. The management of the work at the tunnel face, including the rotation of workers to prevent exhaustion and the provision of rest periods and of fresh air, would have been essential for maintaining the health and the productivity of the workforce. The specific evidence of the working conditions in the tunnel includes the soot deposits on the tunnel ceiling, which were produced by the oil lamps that provided the illumination, and the wear patterns on the tunnel floor, which were produced by the passage of workers and by the dragging of the rock removal equipment. The soot deposits, which are thicker in the sections of the tunnel that were furthest from the entrances and that would have had the poorest ventilation, provide evidence of the specific lighting conditions at different points in the tunnel and of the air quality that the workers experienced. The investigation of the specific techniques that were used to remove the excavated rock from the tunnel face to the surface has been based on the evidence of the tunnel itself and on the comparison with other ancient mining and tunneling operations. The excavated rock, which weighed approximately 2.5 tons per meter of tunnel advance, was probably loaded into baskets or onto wooden boards and carried or dragged by workers along the tunnel to the entrance, where it was deposited on a spoil heap. The narrow dimensions of the tunnel, which were barely wide enough for 2 workers to pass each other, would have required a carefully organized system of one-way traffic, with loaded workers moving toward the entrance and empty workers moving toward the face, to prevent congestion and to maintain the rate of advance. The specific design of the tunnel's cross-section, which is roughly square with dimensions of approximately 1.8 meters by 1.8 meters, appears to have been determined by the practical requirements of the work, rather than by any aesthetic or structural consideration. The height of the tunnel, which is sufficient for a worker to stand upright, would have allowed the workers to cut the rock and to carry the excavated material without the need to crouch or to crawl, reducing the fatigue and the injury risk that would have been associated with a lower tunnel. The width of the tunnel, which is sufficient for 2 workers to pass each other with their loads, would have allowed the efficient flow of workers and materials between the face and the entrance. The specific techniques that were used to maintain the straightness of the tunnel walls, the flatness of the floor, and the consistency of the cross-section along the length of the tunnel are evidence of the quality control that was maintained during the construction. The walls of the tunnel are relatively smooth and relatively straight, with minor irregularities that reflect the specific conditions of the rock at each location, and the floor is relatively flat and relatively level, with the slight slope that was required for the water channel. The consistency of the cross-section along the length of the tunnel suggests that the workers used some form of template or gauge to check the dimensions of the tunnel at regular intervals and to ensure that the cross-section remained within the specified tolerances. The investigation of the specific tool marks on the tunnel walls has revealed that the tunnel workers used 2 distinct cutting techniques, depending on the hardness and the structure of the rock. In the harder, more uniform sections of the tunnel, the workers used a technique of direct percussion, in which the rock was cut by striking it directly with a pointed iron pick, producing a series of parallel grooves that are visible on the tunnel walls. In the softer, more fractured sections of the tunnel, the workers used a technique of indirect percussion, in which an iron chisel was held against the rock face and struck with a hammer, producing a cleaner and more controlled cut that was less likely to cause uncontrolled fracture of the rock. The choice of cutting technique at each location along the tunnel was determined by the specific conditions of the rock, and the ability to adapt the cutting technique to the specific rock conditions is evidence of the practical skill and the experience of the tunnel workers. The question of whether the tunnel workers used any chemical or thermal techniques to assist with the rock cutting, such as the fire setting technique that was used in some ancient mines, has been investigated through the examination of the tunnel walls for evidence of heat damage such as discoloration, cracking, or spalling that would indicate the use of fire. The examination has not produced conclusive evidence of fire setting in the Eupalinos tunnel, and the consensus among researchers is that the tunnel was excavated entirely by mechanical means, using iron picks and chisels, without the assistance of fire or of chemical agents. The total volume of rock that was removed during the construction of the tunnel has been estimated at approximately 7,000 cubic meters based on the measured dimensions of the tunnel and on the estimated volume of the spoil heaps at the two entrances. The 7,000 cubic meters of rock, which weigh approximately 18,000 metric tons, represent an enormous quantity of material that was cut, carried, and disposed of by the tunnel workers over a period of approximately 8 to 10 years. The scale of the excavation, combined with the precision of the alignment and the quality of the construction, makes the Tunnel of Eupalinos one of the most impressive examples of underground construction in the ancient world, and a worthy subject of the admiration that Herodotus expressed when he described it as one of the three greatest works of the Greek world. The specific discovery of iron tool fragments within the spoil heaps at the tunnel entrances has provided direct physical evidence of the tools that were used by the tunnel workers and has allowed the metallurgical analysis of the tool steel that was available to the ancient engineers. The analysis has revealed that the tools were made of a low-carbon iron that was hardened by carburization, a process in which the surface of the iron is enriched in carbon by heating it in contact with charcoal, producing a hard, wear-resistant surface that is suitable for cutting rock. Everything we have discussed so far concerns the specific engineering of the Tunnel of Eupalinos, the specific surveying techniques that were used to achieve the alignment, and the specific scientific investigations that have been conducted to understand how the tunnel was built. These matters are important, and the ongoing research on the tunnel continues to produce new insights into the capabilities of ancient Greek engineering. But beneath these specifics lies a deeper truth, a truth that concerns not just how the tunnel was built, but what its construction tells us about the nature of applied mathematics, the relationship between theory and practice, and the specific conditions that enable the translation of abstract knowledge into physical achievement. The deeper truth is this: the Tunnel of Eupalinos is proof that the ancient Greeks were not merely theorists, they were practitioners. They did not merely discover geometric principles. They applied those principles to the solution of real-world problems of extraordinary complexity and difficulty. The tunnel is a demonstration of applied mathematics at the highest level, a physical monument to the power of geometry to solve practical problems, and its existence challenges the stereotype of the ancient Greeks as abstract thinkers who were more interested in theory than in practice, in philosophy than in engineering, in the contemplation of ideals than in the manipulation of matter. This is not science fiction. This is a physical fact, documented by modern surveys and confirmed by modern measurements, that a Greek engineer of the 6th century before the Common Era used the principles of geometry to achieve a surveying accuracy that would be impressive by modern standards. The tunnel is not a legend, it is not a myth. It is a hole in a mountain, more than a kilometre long, dug from both ends, meeting in the middle with an error of less than a metre, and it has been standing for over 2,500 years as evidence of what the ancient Greeks could do when they applied their mathematical knowledge to a practical problem. Something is wrong with our assumption that the ancient Greeks were primarily theorists who disdained practical application. The Tunnel of Eupalinos demonstrates that the 6th century before the Common Era, the same century that produced the theoretical mathematics of Pythagoras and the natural philosophy of Thales, also produced practical engineering of the highest order. The theoretical and the practical were not separate domains in the 6th century Greek world. They were complementary aspects of a unified intellectual culture that valued both the pursuit of abstract knowledge and the application of that knowledge to the solution of real-world problems. The concept of the applied mathematician, the individual who uses mathematical knowledge to solve practical problems, is one that the Tunnel of Eupalinos demonstrates was present in the ancient Greek world, even though the ancient sources do not explicitly recognize it. Eupalinos was an applied mathematician, a practitioner, who used the principles of geometry to solve the practical problem of aligning a tunnel through a mountain. His mathematical knowledge was not an end in itself. It was a tool, a means to an end, a method for achieving a specific practical result that could not have been achieved without it. The tunnel is a monument to the power of mathematics as a practical tool, and its existence demonstrates that the ancient Greeks recognized and exploited this power in ways that the standard narrative of the history of mathematics does not adequately acknowledge. The relationship between the tunnel of Eupalinos and the other examples of ancient engineering that we have explored in this series provides a comprehensive picture of the engineering capabilities of the ancient world. The series has demonstrated that the ancient world produced engineering achievements in multiple domains, from the precision mechanics of the Antikythera mechanism to the materials science of Roman concrete and Damascus steel, from the nanotechnology of the Lycurgus cup to the corrosion engineering of the Iron Pillar of Delhi. The Tunnel of Eupalinos adds a new domain to this list, the domain of surveying and civil engineering, demonstrating that the ancient world's engineering capabilities extended across an extraordinarily broad range of disciplines, and that the specific achievements in each discipline were at a level that is impressive even by modern standards. The pattern that emerges from these examples is one of distributed excellence, in which different ancient civilizations achieved excellence in different engineering domains, each contributing specific capabilities and specific innovations that were adapted to the specific resources, the specific challenges, and the specific cultural values of each civilization. The Greeks excelled in geometry, in precision mechanics, and in civil engineering. The Romans excelled in concrete, in road building, and in hydraulic engineering. The Indians excelled in metallurgy and in mathematics. The Egyptians excelled in monumental architecture and in materials preservation. The Chinese excelled in ceramics, in metallurgy, and in paper technology. The cumulative picture that emerges from this pattern is one of a global engineering tradition that was far more diverse, far more sophisticated, and far more capable than the standard narrative of the history of technology typically acknowledges. Let that sink in. The ancient world, which is often dismissed as technologically primitive, produced engineering achievements that span the full range of modern engineering disciplines, from materials science to civil engineering, from precision mechanics to hydraulic engineering, from nanotechnology to surveying. The achievements were produced by different civilizations at different times, using different materials and different techniques, but they share a common characteristic. They demonstrate a level of practical capability that is not easily reconciled with the image of the ancient world as a technologically unsophisticated era that was merely a prelude to the modern age. The specific lesson of the Tunnel of Eupalinos for the modern world is the lesson of the power of geometry, the power of mathematical reasoning applied to practical problems. The tunnel was built with no GPS, no laser, no computer, no electronic instrument of any kind. It was built with geometry, with the principles of angles and distances and right triangles that were being formulated by the Greek mathematicians of the 6th century, and that were being applied by the Greek engineers to the most challenging practical problems of the day. The geometry was the technology, the mathematics was the tool, and the result was an engineering achievement that has endured for 25 centuries, and that still impresses every engineer who examines it. The vulnerability of the knowledge that produced the Tunnel of Eupalinos to loss is a theme that connects the tunnel to the other examples of lost and threatened knowledge that we have explored. The specific surveying techniques that Eupalinos used were not documented in any surviving text. They were encoded in the practice of the engineer and in the physical evidence of the tunnel itself, and they have been reconstructed only through the painstaking analysis of the modern surveyors, who have measured the tunnel and who have worked backward from the evidence to infer the methods. If the tunnel had been destroyed, if the mountain had collapsed, or if the tunnel had been deliberately backfilled, the specific knowledge of how Eupalinos achieved the alignment would have been lost, and the standard narrative of the history of surveying would not have been challenged by the evidence of his achievement. The preservation of the tunnel is therefore not merely a matter of archaeological conservation. It is a matter of the preservation of knowledge, of the physical evidence that demonstrates what the ancient Greeks could do, and that challenges the assumptions that the modern world makes about the capabilities of the ancient one. The tunnel is a document. written in stone rather than in words, that records the mathematical and the engineering knowledge of the 6th century before the Common Era, and the preservation of this document is essential for the understanding of the history of human engineering and for the recognition of the achievements of the ancient world. Let that sink in once more. The Tunnel of Eupalinos is a document. It is a record of the mathematical knowledge and the engineering skill of a Greek engineer of the 6th century before the Common Era, written not in ink on papyrus but in rock, in the physical evidence of the tunnel's path, in the specific features of its construction, in the precision of its alignment. The document has survived for 25 centuries, outlasting every papyrus and every parchment of the period, and it continues to provide information about the capabilities of the ancient world that no surviving written text provides. The tunnel is, in a very real sense, the most important surviving text of the 6th century Greek engineering tradition, and its preservation is as important for the understanding of Greek engineering as the preservation of the writings of Herodotus is for the understanding of Greek history. The question of what the Tunnel of Eupalinos tells us about the state of Greek mathematics in the 6th century before the Common Era is one that has been explored by historians of mathematics who have used the tunnel as evidence for the mathematical knowledge that was available to the Greek engineers of the period. The tunnel demonstrates, at a minimum, that the Greek engineers of the 6th century possessed a practical knowledge of geometry that included the ability to measure angles and distances with precision, the ability to calculate the positions of invisible points from the measurements of visible ones, and the ability to establish and to maintain straight lines and constant slopes over long distances in underground environments. The specific mathematical principles that would have been needed for the alignment of the tunnel include the properties of similar triangles, which allow the calculation of unknown distances from known distances and known angles. The Pythagorean theorem, which allows the calculation of the length of the hypotenuse of a right triangle from the lengths of the other two sides. And the properties of parallel lines and transversals, which allow the establishment of parallel lines at a known distance and direction from each other. All of these principles were known in the Greek mathematical tradition by the 6th century before the Common Era, and their application to the surveying problem of the tunnel alignment would have been a natural extension of the theoretical knowledge to a practical context. The question of whether the mathematical knowledge that was available to Eupalinos was sufficient for the precision that was achieved, or whether additional techniques or instruments were needed that are not documented in the surviving sources, is one that has been debated by historians of mathematics and by surveying engineers. The consensus is that the known mathematical principles and the known surveying instruments were sufficient for the precision that was achieved, but that the achievement required an exceptional level of skill and care in the application of these principles and in the use of these instruments. The Tunnel of Eupalinos was not a routine application of standard surveying techniques. It was an exceptional application that pushed the techniques to their limits and that required the specific expertise and the specific judgment of an engineer of exceptional ability. The broader implications of the tunnel for the history of applied mathematics are significant. The tunnel demonstrates that the Greek mathematical revolution of the 6th century before the Common Era, which is typically presented as a purely theoretical achievement that was pursued for its own sake rather than for practical purposes, also had a practical dimension that has been underappreciated in the standard histories of mathematics. The Greek mathematicians of the 6th century were not only discovering abstract principles, they were, through the work of engineers like Eupalinos, applying those principles to the solution of practical problems of the most demanding kind. The history of Greek mathematics is therefore not only a history of theory, it is also a history of practice, and the Tunnel of Eupalinos is one of the most impressive surviving examples of this practical dimension. The question of whether the specific techniques that Eupalinos used were his own invention, or whether they were part of an established tradition of Greek surveying practice, is one that cannot be answered from the available evidence. The absence of contemporary written accounts of Greek surveying techniques means that we do not know whether Eupalinos developed his techniques independently, or whether he learned them from a teacher or from a manual of surveying practice. The possibility that there was a tradition of Greek surveying practice that included the specific techniques that Eupalinos used, a tradition that was transmitted through the apprenticeship system and that was applied to a variety of construction projects, is plausible but unproven, and the evidence of the tunnel itself is consistent with both the hypothesis of individual invention and the hypothesis of transmitted tradition. The philosophical dimension of the tunnel of Eupalinos has been explored by scholars who have seen in the tunnel a physical manifestation of the Greek philosophical principle that the universe is ordered by mathematical laws and that the understanding of these laws provides the key to the mastery of the physical world. The pre-Socratic philosophers, who were the contemporaries of Eupalinos and who were engaged in the radical project of explaining the natural world through reason rather than through myth, would have seen the tunnel as a confirmation of their fundamental conviction that nature is rational, that its behavior can be predicted by mathematical calculation, and that the human mind is capable of understanding and of controlling the natural world through the power of reason. The connection between the pre-Socratic philosophical project and the engineering project of the tunnel is not merely metaphorical. The pre-Socratic philosophers, particularly Thales of Miletus, who is credited with the introduction of deductive geometry into the Greek mathematical tradition, and Pythagoras of Samos, who is credited with the theorem that bears his name and with the discovery of the mathematical relationships that underlie musical harmony, were developing the specific mathematical tools that Eupalinos would have needed for the alignment of the tunnel. The tunnel is, in a very real sense, a product of the pre-Socratic intellectual revolution, a physical demonstration of the power of the mathematical principles that the pre-Socratic philosophers were discovering. The French philosopher Paul Valéry, writing in the 20th century, used the tunnel of Eupalinos as the central metaphor for his dialogue, Eupalinos, or the Architect, a philosophical meditation on the relationship between mathematics, architecture, and the human soul. Valéry's dialogue, which presents a conversation between Socrates and Phaedrus in the afterlife, uses the figure of Eupalinos as a model for the ideal relationship between theory and practice, between mathematical understanding and physical creation, between the contemplation of abstract principles and the making of objects in the physical world. Valéry's use of Eupalinos as a philosophical symbol testifies to the enduring power of the tunnel as a metaphor for the relationship between thought and action, between knowledge and creation. The specific question of how the tunnel of Eupalinos fits into the broad history of infrastructure development in the ancient world provides additional perspective on its significance. The ancient world invested enormous resources in the construction of infrastructure, including roads, bridges, aqueducts, harbours, canals, and fortifications that served the military, commercial, and civilian needs of the ancient civilizations. The specific investment in water supply infrastructure, including the aqueducts and the tunnels that supplied water to the cities of the ancient world, was one of the most important categories of ancient infrastructure investment, because the availability of a reliable water supply was essential for the survival and the prosperity of the urban communities that depended on it. The tunnel of Eupalinos is one of the earliest surviving examples of this type of infrastructure investment in the Greek world, and its construction marks a significant milestone in the development of the engineering capabilities that would be used in the following centuries to construct the much larger and much more complex water supply systems of the Hellenistic and the Roman periods. The Roman aqueduct system, which supplied water to the city of Rome through a network of channels, tunnels, and bridges that extended for approximately 500 kilometers, is the most famous example of ancient water supply infrastructure. And the engineering knowledge that was used to build the Roman aqueducts can be traced, in part, to the earlier Greek tradition, of which the Eupalinos tunnel is the most impressive surviving example. The question of whether the knowledge that Eupalinos used to build the tunnel was transmitted to subsequent generations of Greek engineers, or whether it was lost with Eupalinos himself, is one that connects the tunnel to the broader theme of knowledge preservation and knowledge loss that has been a recurring theme in this series. The evidence suggests that the specific surveying techniques that Eupalinos used were, in some form, transmitted to subsequent generations because the Greek and the Roman engineers who built tunnels and aqueducts in the following centuries achieved levels of precision that are comparable to those of the Eupalinos tunnel. The Roman engineer Vitruvius, writing in the 1st century before the Common Era, described surveying techniques for tunnel alignment that are consistent with the techniques that Eupalinos is believed to have used, including the use of traverse surveys, the use of the groma for angle measurement, and the use of the chorobates for levelling. The fact that Vitruvius described these techniques approximately 450 years after the construction of the Eupalinos tunnel suggests that the techniques were part of an established tradition of engineering practice that was transmitted from one generation of engineers to the next over a period of several centuries. The question of whether the knowledge was transmitted in written form or in oral form is one that has implications for the vulnerability of the knowledge to loss. The written transmission of technical knowledge, which involves the recording of the knowledge in a text that can be copied and distributed, provides a more durable and a more widely accessible form of preservation than the oral transmission, which involves the verbal instruction of an apprentice by a master, and which is vulnerable to interruption if the chain of transmission is broken. The evidence suggests that both forms of transmission were used in the ancient world, with the written texts of Vitruvius and of other ancient engineers providing a permanent record of the techniques, while the oral tradition of the engineering apprenticeship provided the practical skill and the experiential knowledge that were needed to apply the techniques in the field. The loss of the ancient engineering traditions, which occurred during the decline of the Roman Empire, and the subsequent disruption of the institutional structures that had sustained the engineering profession, resulted in the loss of much of the specific knowledge that the ancient engineers had accumulated. The specific surveying techniques that Eupalinos used, while they were described in general terms by Vitruvius and by other ancient writers, were not described in the detailed, step-by-step form that would have been needed for their reproduction by someone who did not have access to the oral tradition of the engineering profession. The loss of the oral tradition, which occurred when the engineering profession declined and the apprenticeship system was disrupted, resulted in the loss of the specific practical knowledge that was needed to apply the techniques described in the written texts. The rediscovery of the ancient surveying techniques, which occurred during the Renaissance and the early modern period, through the study of the ancient texts and through the independent development of new surveying instruments and techniques, was a gradual process that extended over several centuries, and that was driven by the practical needs of the expanding European cities and the expanding European colonies. The specific techniques that Eupalinos used were not rediscovered until the modern era, when the detailed survey of the tunnel by Kianast and by other researchers revealed the specific features of the tunnel's alignment that allowed the reconstruction of the surveying methods. The specific contribution of the tunnel of Eupalinos to the field of geoarchaeology, the study of the geological context of archaeological sites, has been significant because the tunnel provides a unique cross-section through the geology of Mount Kastro that has been used by geologists to study the specific rock types, the geological structures, and the groundwater conditions of the mountain. The geological information that the tunnel provides, which would otherwise be available only through expensive and time-consuming drilling programs, has been used to reconstruct the geological history of the mountain and to understand the specific geological conditions that influenced the construction and the preservation of the tunnel. The specific rock types that are exposed in the tunnel walls include several varieties of limestone, ranging from the dense, uniform limestone that makes up the majority of the tunnel's length to the softer, more fractured limestone that is found in the fault zones and in the zones of intense weathering. The variation in rock type along the tunnel's length would have influenced the rate of advance and the specific techniques that were used by the tunnel workers, with the harder rock requiring more effort to cut and the softer rock requiring more care to prevent collapse. The groundwater conditions within the mountain, which have been studied through the observation of water seepage in the tunnel and through the analysis of the mineral deposits that have formed on the tunnel walls, provide information about the hydrological conditions that existed during the tunnel's use as an aqueduct. The mineral deposits, which include calcite, gypsum, and various iron oxide minerals, have been formed by the evaporation of groundwater on the tunnel walls, and their composition provides information about the chemistry of the groundwater and about the rate at which the water was flowing through the mountain. The long-term geological stability of the tunnel, which has been maintained for over 2,500 years, despite the seismic activity of the eastern Aegean region, is a consequence of the specific geological conditions of Mount Kastro and of the specific route that Eupalinos chose for the tunnel. The route avoids the major fault zones that traverse the mountain, and the specific rock type that predominates along the route is a dense, uniform limestone that is resistant to seismic damage. The choice of the route, which was probably informed by a geological survey of the mountain that Eupalinos conducted before the construction began, demonstrates the importance of geological knowledge in the design of underground structures and provides evidence that the ancient engineers possessed a practical understanding of the geological conditions that influence the stability of tunnels. The connection between the tunnel of Eupalinos and the modern discipline of tunnel engineering provides a perspective that illuminates both the ancient achievement and the modern practice. The modern tunnel engineer, who uses computer models, laser surveying, and tunnel boring machines to design and to construct tunnels, works within a tradition that has its roots in the ancient practice of tunnel construction and the specific challenges that the modern tunnel engineer faces, including the alignment of tunnels through mountains, the management of groundwater, and the stabilization of weak rock, are the same challenges that Eupalinos faced 25 centuries ago. The tunnel of Eupalinos, which is one of the earliest and one of the most impressive examples of tunnel engineering in the historical record, provides a starting point for the understanding of the development of the engineering discipline that has produced the tunnels of the modern world. The modern educational use of the tunnel of Eupalinos as a case study in the teaching of engineering, mathematics, and the history of technology has been developed by educators who have recognized the tunnel's unique combination of mathematical interest, engineering complexity, and historical significance. The tunnel provides an ideal case study because it is small enough to be comprehended by a single student, complex enough to illustrate the fundamental principles of surveying and tunnel engineering, and well documented enough to allow the specific methods that were used to be analyzed and evaluated. The specific educational applications of the tunnel include the use of the alignment problem as an exercise in applied geometry, in which students are asked to devise a surveying method for the alignment of a tunnel through a mountain, given the specific constraints and the specific instruments that were available to Eupalinos. The exercise, which requires the students to apply the principles of geometry to a real-world problem with specific constraints and specific sources of error, provides a powerful demonstration of the practical utility of mathematical knowledge and of the specific challenges that arise when abstract principles are applied to physical problems. The use of the tunnel as a case study in the history of technology has also been developed by educators who have used the tunnel to illustrate the broader themes of the relationship between theory and practice, between individual expertise and institutional support, and between the ancient and the modern approaches to engineering. The tunnel provides a concrete and a compelling example of each of these themes, and its story engages students in a way that abstract discussions of the same themes often do not. The publication of the Kinas survey and the subsequent analyses in accessible formats, including popular books, documentary films, and educational websites, has made the story of the tunnel available to a wide audience and has contributed to the public recognition of the tunnel as one of the most important engineering achievements of the ancient world. The story of the Tunnel of Eupalinos is one that has the power to inspire, to educate, and to challenge, and the continued dissemination of the story to new audiences is one of the most valuable contributions that the scholarly community can make to the public understanding of the ancient world and of the history of engineering. The question of what the Tunnel of Eupalinos would have looked like to the ancient visitor, walking through the passage from one side of the mountain to the other, carrying an oil lamp and following the sound of water flowing through the channel at his feet, is one that connects the engineering achievement to the human experience of the tunnel. The tunnel was not merely a technical achievement, it was a physical space, a passage through the mountain that was used by the people who maintained the water supply system, and, possibly, by other travelers who used the tunnel as a shortcut from one side of the mountain to the other. The experience of walking through the tunnel, which takes approximately 20 to 30 minutes at a walking pace, would have been a powerful and a memorable one. The darkness of the tunnel, which is absolute beyond the reach of the oil lamp's glow, the coolness of the air, the sound of water flowing through the channel, and the claustrophobic narrowness of the passage would have combined to create a sensory experience that was fundamentally different from the experience of the surface world. The tunnel would have been a liminal space, a boundary between the two sides of the mountain and between the two worlds that the mountain separated, and the experience of passing through it would have been both practical and symbolic. What does the Tunnel of Eupalinos mean for our understanding of the relationship between mathematics and engineering, between theory and practice, and between the ancient and the modern approaches to the solution of technical problems? The first implication is a recognition that the distinction between theoretical and applied knowledge is not as sharp as we typically assume, and that the ancient Greek world, which is conventionally associated with theoretical knowledge, was also a world of practical application. The Tunnel of Eupalinos demonstrates that the Greek mathematicians of the 6th century before the Common Era were not only discovering abstract principles, but were also applying those principles to the solution of practical problems of extraordinary difficulty. The tunnel is a physical manifestation of abstract geometry, a three-dimensional proof of the practical power of mathematical reasoning. The second implication is a recognition of the importance of individual expertise in the achievement of complex engineering projects. The Tunnel of Eupalinos was designed by a single engineer, Eupalinos, whose specific knowledge, specific skills, and specific judgment were essential for the success of the project. The tunnel was not the product of a committee or a bureaucracy. It was the product of an individual mind that possessed the specific combination of mathematical knowledge, surveying skill, and practical engineering judgment that was needed to solve a problem that had never been solved before. The importance of individual expertise in the achievement of complex engineering projects is a lesson that is as relevant to the modern world as it was to the ancient one, and the Tunnel of Eupalinos is one of the earliest and most impressive demonstrations of this principle. There is a pause worth taking here. Consider Eupalinos, standing at the south entrance of the tunnel, looking into the darkness of the mountain, knowing that his calculations must be correct, that his survey must be accurate, that the direction he has given to the diggers must be precisely right. Because if it is wrong, the two tunnels will miss each other and the project will fail. Consider the weight of that responsibility, the pressure of knowing that the success or the failure of the most ambitious engineering project in the Greek world depends on the accuracy of his calculations and the precision of his measurements. Consider the courage that it took to commit to the calculations, to give the order to start digging, and to trust that the mathematics would be vindicated by the physical reality of the rock. The third implication is a challenge to the notion that engineering progress is a continuous, cumulative process in which each generation builds upon the achievements of the previous generation. The Tunnel of Eupalinos was built in the 6th century before the Common Era, and it was one of the most impressive surveying achievements in the history of engineering. The tunnels that were built in the subsequent centuries including the Roman tunnels that were built using more advanced instruments and more sophisticated techniques, did not dramatically exceed the accuracy that Eupalinos achieved. The progress from the Eupalinos tunnel to the modern tunnel is not a smooth, continuous curve of improvement, but a series of discrete advances, each of which was made possible by specific innovations in instruments, in techniques, and in mathematical knowledge, separated by long periods of relative stagnation. The fourth implication is a reflection on the relationship between necessity and innovation. The tunnel of Eupalinos was built because the water supply of the city of Pythagorean was a strategic vulnerability that needed to be protected from enemy attack. The necessity drove the innovation, forcing Eupalinos to develop and to apply surveying techniques that were at the very limit of what was possible with the instruments and the knowledge that were available to him. The relationship between necessity and innovation, which is a recurring theme in the history of technology, is illustrated with particular clarity by the tunnel of Eupalinos, because the specific necessity, the protection of the water supply, drove the specific innovation, the development of precise surveying techniques for tunnel alignment in a direct and traceable way. The fifth implication concerns the modern conservation and the educational use of the tunnel. The tunnel of Eupalinos, which is now a UNESCO World Heritage Site, provides an extraordinary educational resource for the teaching of ancient engineering, of the history of mathematics, and of the application of mathematical principles to practical problems. The tunnel allows visitors to walk through the physical evidence of Eupalinos' achievement, to see the tool marks on the rock face, to observe the point where the two tunnels meet, and to appreciate the scale and the difficulty of the project in a way that no textbook or lecture can convey. The educational value of the tunnel is one of the strongest arguments for its continued conservation and for the investment of resources in its maintenance and its presentation to the public. The global cost of infrastructure failure, which runs into the trillions of dollars annually, provides a modern context for the appreciation of the tunnel of Eupalinos' achievement. The tunnel has been in existence for over 2,500 years, and its structural integrity has been maintained throughout this period with minimal maintenance. The modern infrastructure of bridges, tunnels, roads, and buildings, which is designed to last for decades rather than for centuries, requires constant maintenance and periodic replacement at enormous cost. The comparison between the longevity of the Eupalinos tunnel and the limited lifespan of modern infrastructure raises questions about the design priorities and the construction standards of the modern world, questions that the ancient tunnel answers by its simple, enduring existence. The sixth implication concerns the relationship between risk and innovation in engineering. The decision to build the tunnel of Eupalinos was a decision that involved significant risk, because the failure of the alignment would have resulted in the waste of years of labour and enormous financial resources. The willingness to accept this risk on the part of both the patron, Polycrates, and the engineer, Eupalinos, demonstrates a confidence in the power of mathematical calculation that is itself impressive and that speaks to the intellectual culture of the 6th century Greek world. The confidence was justified by the result, but the decision to accept the risk before the result was known was an act of intellectual courage that deserves recognition. The relationship between risk and innovation is a theme that connects the tunnel of Eupalinos to the broader history of engineering, in which the most impressive achievements have often been accomplished by engineers who were willing to accept the risk of failure in pursuit of an ambitious goal. The willingness to accept risk is a precondition for innovation, because innovation, by definition, involves the attempt to achieve something that has not been achieved before, and the outcome of such an attempt is always uncertain. The tunnel of Eupalinos is an example of an innovation that succeeded, but the history of engineering also includes many examples of innovations that failed, and the failures are as instructive as the successes, because they illustrate the limits of the specific techniques and the specific materials that were available at the time. The seventh implication of the Eupalinos tunnel story concerns the relationship between ancient and modern standards of engineering precision. The modern engineering profession uses a system of standards, specifications, and quality control procedures that ensure that engineering projects meet specific requirements for accuracy, for safety, and for performance. The ancient engineering profession did not use a comparable system of formal standards, and the quality of ancient engineering projects was determined primarily by the skill and the judgment of the individual engineers and the individual workers who executed the projects. The comparison between the precision of the Eupalinos tunnel and the precision of modern tunnel projects reveals that the ancient engineer, working without formal standards and without the precision instruments of the modern era, achieved a level of accuracy that is comparable to the accuracy that is achieved by modern engineers working with far more advanced technology. The 60-centimeter horizontal error and the 30-centimeter vertical error at the meeting point of the Eupalinos tunnel are within the range of errors that are accepted in modern tunnel construction, where the typical tolerance for the meeting of two tunnel faces is approximately 10 to 50 centimeters, depending on the specific requirements of the project. The fact that Eupalinos achieved a level of precision that is within the range of modern tolerances, using instruments and techniques that are far less precise than modern instruments, is a testament to his skill and to the effectiveness of his surveying methods. The comparison also raises the question of whether the modern engineering profession, with its reliance on technology and its adherence to formal standards, has lost some of the individual skill and the individual judgment that characterize the ancient engineering tradition. The modern engineer, who relies on GPS, on laser surveying, on computer-aided design, and on a host of other technological tools, may be less skilled in the fundamental techniques of surveying and of engineering judgment than the ancient engineer, who had to rely on simple instruments and on his own mathematical ability to achieve the required precision. The question is not whether modern technology is superior to ancient technology, which it clearly is, but whether the reliance on technology has reduced the development of the fundamental skills that would be needed if the technology were not available. The eighth implication of the Eupalinos tunnel story concerns the relationship between individual achievement and institutional support in the execution of complex engineering projects. The tunnel of Eupalinos was designed by a single engineer, but it was built by a large team of workers who were organized and managed by an institutional structure that provided the resources, the logistics, and the coordination that were needed for the successful execution of the project. The individual genius of Eupalinos, while it was essential for the design of the tunnel and for the solution of the alignment problem, would have been insufficient without the institutional support that the Polycratic state provided. The specific institutional structures that supported the construction of the tunnel included the administrative apparatus of the Polycratic state, which mobilized the labor and the resources that were needed for the project, the supply chain that provided the tools, the fuel, the food, and the other materials that were needed for the construction, the management system that coordinated the work of the two tunnel teams, and that ensured that the construction proceeded according to the plan, and the quality control system that monitored the alignment and the dimensions of the tunnel during the construction, and that detected and corrected any deviations from the plan. The importance of institutional support for the execution of complex engineering projects is a lesson that is as relevant to the modern world as it was to the ancient one. The modern engineering projects that are the most impressive and the most consequential, from the construction of the International Space Station to the development of the global telecommunications network, are the products of institutional structures that provide the resources, the coordination, and the management that are needed for the successful execution of projects that are beyond the capabilities of any individual, however talented. The Tunnel of Eupalinos is one of the earliest and one of the most impressive examples of the partnership between individual genius and institutional support that is the hallmark of successful engineering projects, and the tunnel's survival for 25 centuries is a testament to the effectiveness of this partnership and to the quality of the work that it produced. The ninth implication of the Eupalinos tunnel story concerns the recognition of the specific intellectual achievement that the tunnel represents. The alignment of the tunnel was not merely a technical achievement. It was an intellectual achievement, a triumph of mathematical reasoning over the physical constraints of the mountain, a demonstration that the human mind can solve problems that the human body cannot. The mountain was an obstacle, a barrier of solid rock that separated the two sides of the island and that blocked the flow of water from the spring to the city. Eupalinos solved this problem not by moving the mountain, but by thinking through it, by using the abstract principles of geometry to calculate a path through the rock that would connect the two sides, and by using the practical techniques of surveying and of rock cutting to realize that calculated path in physical reality. The intellectual dimension of the tunnel's construction is often overlooked in favor of the physical dimension, the labor of the workers, the hardness of the rock, the darkness and the dust of the underground workspace. But the intellectual dimension is the more fundamental one, because without the mathematical calculations that determined the tunnel's path, the physical labor would have been wasted, the workers would have dug in the wrong direction, and the two tunnels would never have met. The intellectual achievement came first, and the physical achievement followed from it. The tunnel is, in its essence, a thought made real, an abstraction given physical form, a calculation carved in stone. The recognition of the intellectual dimension of ancient engineering achievements is one of the most important lessons that the Tunnel of Eupalinos teaches. The ancient engineers are often portrayed as craftsmen rather than as intellectuals, as practitioners rather than as thinkers, as people who worked with their hands rather than with their minds. The Tunnel of Eupalinos challenges this portrayal because it demonstrates that the ancient engineers were thinkers as well as practitioners, that their achievements were the products of mathematical reasoning as well as of physical labor, and that the line between the intellectual and the practical, between the theoretical and the applied, was no sharper in the ancient world than it is in the modern one. The Tunnel of Eupalinos passes through the mountain in silence. The water that once flowed through the channel on its floor has long since been diverted to other paths, and the tunnel is dry now, its walls dark and cool, its air still and quiet. The tool marks of the ancient diggers are still visible on the rock face, the grooves and the furrows of the iron picks and the chisels that cut the limestone 2,500 years ago. The marks are the handwriting of anonymous workers, men whose names are not recorded in any text, men who spent years in the dark, cutting rock, carrying baskets, breathing dust, following the direction that Eupalinos had calculated and that they trusted with their lives. The meeting point of the two tunnels is marked by a slight change in the direction of the passage, a gentle curve where the north team and the south team adjusted their headings in the final meters, guided by the sound of each other's picks through the thinning rock. The curve is subtle, barely noticeable to the casual visitor, but to the engineer who understands what it represents, it is one of the most dramatic moments in the history of ancient engineering. The moment when two teams of workers, who had been digging toward each other for years, through hundreds of meters of solid rock, heard the first faint sounds of each other's work and knew that the tunnel would connect. The math is striking. 1,036 meters of tunnel, two teams digging from opposite sides, less than 60 centimeters of horizontal error, less than 30 centimeters of vertical error. No GPS, no laser, no computer, only geometry, only the angles and the distances that Eupalinos calculated using the principles that the Greek mathematicians of his generation were just beginning to formulate. The geometry was enough, the mathematics was sufficient. The ancient knowledge, applied with skill and with courage, produced a result that has endured for 25 centuries, and that continues to astonish every modern engineer who examines it. The tunnel does not advertise its achievement. It does not proclaim its precision or its longevity or its significance for the history of engineering. It simply exists, a passage through a mountain, a channel for water, a solution to a problem that was posed 2,500 years ago by a tyrant who needed to protect his city's water supply. The solution worked. The water flowed, the city was supplied, and the tunnel, the physical embodiment of Eupalinos' mathematics and of the workers' labor, has outlasted the tyrant, the city, the civilization, and the specific problem that it was designed to solve. Herodotus, writing a century after the tunnel was built, called it one of the three greatest works of the Greek world. He was not wrong. The Tunnel of Eupalinos is one of the greatest engineering achievements of antiquity, a work that demonstrates the power of mathematics to solve practical problems, the skill of ancient engineers to execute complex projects with limited tools, and the capacity of human intelligence to achieve feats that seem impossible when you stand at the entrance of the tunnel and look into the darkness of the mountain. The darkness stretches ahead, more than a kilometer of passage through solid rock, dug by hand, aligned by geometry, meeting in the middle with a precision that defies the expectations of anyone who assumes that the ancient world could not match the technical capabilities of the modern one. The tunnel is an answer to that assumption, an answer that is carved in stone and that has been waiting for 2,500 years to be heard. The water that once flowed through the tunnel carried the life of the city. The tunnel that carried the water carries something else, the knowledge that the people who came before us, working with simple tools and with the power of geometry, could achieve things that we, with all our technology, still find difficult to believe. The Tunnel of Eupalinos is that knowledge, made physical, made permanent, made indestructible by the simple fact of its existence. The tunnel is there, the meeting point is there, the precision is there, and the question that the tunnel answers, the question of what the ancient world could do, is answered by the stone itself, in a language that needs no translation, and that speaks as clearly today as it did 25 centuries ago. The tunnel is more than a passage through a mountain. It is a passage through time, connecting the modern visitor to the world of the 6th century before the Common Era, to the world of Polycrates and Eupalinos, of Pythagoras and the pre-Socratic philosophers, of the archaic Greek city-states, and the nascent scientific revolution that was beginning to transform the Greek understanding of the natural world. The visitor who walks through the tunnel walks through the same space that the ancient workers carved from the rock, breathes air that flows through the same passage, touches walls that bear the marks of the same tools. The experience is immediate and visceral, a direct physical connection to the ancient world that no museum display and no written text can replicate. The tunnel is also a monument to the anonymous workers who dug it, the men whose names are not recorded in any text but whose labor created the physical reality that Eupalinos designed. The tool marks on the rock face are the evidence of their work, the grooves, and the scars of the iron picks that they wielded for hours each day, in the dark, in the dust, in the confined space of the tunnel face. The workers are invisible in the historical record, but they are present in the tunnel, in the physical evidence of their labor that has been preserved in the rock for 25 centuries. The Tunnel of Eupalinos is a reminder that the great achievements of engineering are always the products of collaboration, of the partnership between the visionary who conceives the project and the workers who execute it, between the mathematician who calculates the alignment and the miner who cuts the rock, between the patron who provides the resources and the manager who coordinates the effort. The tunnel is credited to Eupalinos, as it should be, because his was the mind that solved the alignment problem and that designed the engineering system that made the tunnel possible. But the tunnel is also the product of the labor of hundreds of anonymous workers, and their contribution to the achievement is as essential as the contribution of the engineer. The tool marks on the walls of the tunnel are a language, a record of the labor and the skill of the workers who carved the passage through the mountain. Each mark represents a single stroke of a pick or a chisel, a single moment of effort that removed a small fragment of rock from the tunnel face, and that brought the tunnel a fraction of a centimeter closer to completion. The marks accumulate over the length of the tunnel, millions of individual strokes, each one directed by the worker's hand and guided by the worker's eye, each one contributing to the slow, steady advance of the tunnel face through the mountain. The marks are also a clock, recording the passage of time in the underground darkness, the days and the months and the years that the workers spent in the mountain, cutting rock, carrying baskets, following the direction that Eupalinos had calculated and that they trusted. The workers lived in the mountain for years, spending their days in the narrow, dim passage, breathing the dusty air, feeling the cool rock beneath their hands, listening to the rhythmic sound of the picks striking the stone, a sound that filled the tunnel for years and that stopped, finally, when the picks of the south team and the picks of the north team were close enough to hear each other through the rock, signaling that the moment of meeting was near. The tunnels is a testament to the enduring power of mathematics, to the conviction that the laws of geometry are not merely abstract truths but practical tools that can be used to shape the physical world. The pre-Socratic philosophers who were developing the mathematical principles that Eupalinos applied believed that the universe was governed by mathematical laws, and the tunnel is the physical proof of their belief. The tunnel is geometry made real, measurement made stone, calculation made passage, the abstract principles of angles and distances and right triangles given physical form in a kilometre of carved limestone. The story of the Tunnel of Eupalinos is the story of a civilization that believed in the power of reason, that trusted the calculations of its engineers, and that invested the resources and the labour that were needed to translate those calculations into physical reality. The story is 25 centuries old, but its message is as relevant today as it was when the two teams of workers heard each other's picks through the thinning rock and knew that the tunnel would connect. Mathematics works, geometry is real, calculation is power, and the human mind, armed with the tools of mathematical reasoning, can see through mountains and can achieve the seemingly impossible.